You are about to find out that everything we have ever sent to Saturn was, from the moment of launch, intended to stay there. Not as a failure. As a feature. The 4 spacecraft that have reached Saturn, Pioneer 11, Voyager 1, Voyager 2, and Cassini, were all one-way missions by design. 3 of them simply flew past and continued into deep space. The 4th, Cassini, was deliberately driven into Saturn's atmosphere at the end of its mission and destroyed. None of them was ever planned to come back. Not because we were not ambitious enough, because the math of returning from Saturn, as opposed to going there, is so brutally different from the math of return missions inside the inner solar system that the entire mission architecture changes. Going to Saturn is a difficult mission. Coming back from Saturn is not a mission at all. It is a thought experiment that no aerospace engineer has ever taken to a serious design level. This is what we are walking through tonight. Why Saturn was always a one-way destination, and why the first humans who eventually go almost certainly will not be exceptions. If these slow cosmic walks help you settle before sleep, a quiet subscribe means a lot. We begin. On September 15, 2017, in a control room at the Jet Propulsion Laboratory in Pasadena, California, a group of engineers gathered to deliberately destroy a spacecraft they had spent 20 years building, operating, and learning from. The spacecraft was 43 billion kilometers from where they sat. It was still functional. It still had power. It was still sending back data, including a final stream of measurements about Saturn's atmosphere taken in the last minutes of its existence. And the engineers, knowing all of this, sent a command that ended it. They had no other option. The spacecraft was called Cassini. It had launched on October 15, 1997, from Cape Canaveral, Florida, aboard a Titan IV-B rocket. It weighed 5,720 kilograms at launch, including its fuel, the Huygens probe attached to its side, and its scientific instruments. It was approximately the size of a small school bus. It carried 12 scientific instruments designed to study Saturn, its rings, and its moons in detail no spacecraft had ever attempted before. The trip took almost 7 years. Cassini flew past Venus twice, in 1998 and 1999, picking up speed through gravity assists. It flew past Earth on August 18, 1999, receiving a final boost of 55 kilometers per second from our own planet's gravity. It flew past Jupiter in December 2000, getting one more push, and finally arrived at Saturn on July 1, 2004. For 13 years after arrival, Cassini orbited Saturn. It dropped the European-built Huygens probe onto the surface of Titan, the largest moon, in January 2005, achieving the first and so far only landing on any world in the outer solar system. It mapped Saturn's rings in detail no telescope had ever managed. It discovered geysers shooting from the south pole of Enceladus. It found evidence of a global subsurface ocean inside that small icy moon. It took 453.48 photographs. It returned 635 gigabytes of scientific data, and throughout all of this the spacecraft was running on a fixed amount of fuel. When Cassini launched, it carried 2,978 kilograms of propellant. By 2017, it had used almost all of it. By the time the engineers had to decide what to do with the spacecraft at end of mission, only about 1% of the original propellant remained. Without fuel, the spacecraft would have continued in its orbit around Saturn for an indeterminate period, and eventually, given the gravitational influences of Saturn's many moons, it would have either drifted into one of them or been ejected from the Saturn system entirely. This created a problem the engineers took seriously, and which deserves a moment of attention. The problem was called planetary protection. 2 of Saturn's moons, Titan and Enceladus, are considered candidate locations for microbial life elsewhere in our solar system. Both have liquid water environments that, under the right conditions, could potentially harbour microorganisms. If Cassini, carrying any contamination from Earth, were to crash into either of those moons, the contamination could compromise future scientific efforts to search for indigenous life. The international scientific community considers this kind of contamination a serious ethical issue, so the engineers chose the only option that guaranteed protection. They sent Cassini into Saturn itself. The planet's enormous atmosphere would burn the spacecraft completely, no contamination would survive. The decision was made years in advance. The trajectory was planned. The final orbit was designed to bring Cassini close to the planet at the right angle for atmospheric entry. The end came at 11:55 a.m. Pacific Time on September 15, 2017. The spacecraft transmitted data until the last possible moment, fighting its small thrusters against the increasing atmospheric drag, then lost contact as it heated and disintegrated. What the engineers did was not unusual in the history of space exploration. They did what every Saturn mission has had to do in different forms. They accepted that whatever they sent to Saturn was not coming back. Saturn is, on average, 1.43 billion kilometres from Earth. This is a number that almost nobody, when they first encounter it, feels in any meaningful way. It is too large. The mind reads it as very far and moves on. But if you slow down and let the comparison fill in, the distance starts to acquire a different kind of weight. The Moon is 384,400 kilometers from Earth. Saturn, on average, is about 300 and 720 times farther than the Moon. To put that another way, you could line up 3,720 Earth-Moon distances end to end and only just begin to span the gap to Saturn. Mars, the destination of most modern human spaceflight planning, is on average about 226 million kilometers from Earth. Saturn is roughly 3 times farther than Mars on average, and up to 8 times farther at maximum separation. Everything that makes Mars a 7-month journey at minimum becomes a 7-year journey when applied to Saturn, because the distance is in a categorically different range. The distance to Saturn is also not constant. Earth and Saturn both orbit the Sun, and their orbital periods are very different. Earth completes its orbit in 1 year. Saturn takes 29 5-Earth years to complete one orbit around the Sun. Because of this, the relative positions of the two planets shift continuously. When Earth and Saturn happen to be on the same side of the Sun and aligned in their orbits, the distance between them shrinks to approximately 2 billion kilometers, sometimes a bit less. This is the closest approach. When they are on opposite sides of the Sun, the distance grows to roughly 1.7 billion kilometers. This is the maximum separation. The 143 billion kilometer average is what you get when you integrate across the full range of possible positions. It is the number that appears in textbooks and reference materials. It is the number that any real mission has to plan around, because by the time a spacecraft arrives, the geometry has shifted from whatever it was at launch. Let me try one more comparison. The Earth is about 12,742 kilometers in diameter. Saturn, at average distance, is roughly 112,000 Earth diameters away. If you shrunk the Earth to the size of a tennis ball, about 7 centimeters across, Saturn at average distance would be about 75 kilometers away. A long walk, a walk of more than an hour, just to cover the model distance, at human walking speed, where the Earth is a tennis ball, and at the speeds we can build for real spacecraft, this distance is what we have to cross. Not in tennis ball units, in real units. 43 billion kilometers, at speeds that physics and chemistry permit, with fuel that has to be carried from Earth or harvested from the journey itself. This is the first thing the title of tonight's conversation is hiding. The distance is not a bit farther than Mars. It is in a different category. Mars distances are inner solar system distances ranging up to a few 100 million kilometers. Saturn distances are outer solar system distances measured in billions. The unit changes, the mental model has to change with it. And it gets worse because Saturn is not even close to the farthest planet. Uranus is twice as far as Saturn. Neptune is 3 times as far. Pluto, when it is at its average distance, is about 4 times as far. The outer solar system is a place where distances scale up logarithmically, and the further out you go, the more impossible the math becomes. Saturn is, in a way, the last planet that is still in the same conceptual range as something we might consider visiting. Everything beyond Saturn is, for all practical purposes, beyond our current category of consideration. And even Saturn, as you will see, is right at the edge of what is plausible. The solar system has a structure that becomes important once you start thinking about interplanetary travel. The inner solar system, the part closest to the Sun, contains 4 rocky planets: Mercury, Venus, Earth, and Mars. These planets sit relatively close to each other in cosmic terms. The distance between Earth and Mars is, on average, less than the distance between Earth and the Sun. The inner planets all orbit within roughly 1.5 times the Earth-Sun distance from the Sun itself. Beyond Mars, there is a gap, a region containing millions of asteroids called the asteroid belt, which extends from about 22 to about 32 times the Earth-Sun distance. This gap separates the inner solar system from what comes next. What comes next is the outer solar system, the gas giants: Jupiter, Saturn, Uranus, Neptune. These planets are not rocky. They are vast spheres of hydrogen and helium with deep atmospheres and complex interior structures. They are far larger than any of the inner planets, and they orbit at far greater distances. Saturn is the second of the gas giants. It orbits the Sun at an average distance of approximately 1.43 billion kilometres, which works out to about 9.5 times the Earth-Sun distance. By comparison, Jupiter orbits at about 5.4, 2 times the Earth-Sun distance, and Uranus at about 19 times. Saturn sits in the middle of this outer shelf, far from both the inner planets and from Uranus and Neptune. The orbital period of Saturn is approximately 29.5 Earth years. This means that Saturn completes one trip around the Sun in the time it takes Earth to complete 29.5 trips. If you were born when Saturn was at one position in its orbit, the planet would not return to that same position until your 30th birthday. A human lifespan, by Saturnian standards, is short. Roughly 2.5 Saturn years is short. Roughly 2.5 Saturn years. This long orbital period has consequences for missions. Because Saturn moves so slowly through the sky relative to Earth, the relative positions of the two planets shift slowly. The launch window from Earth to Saturn occurs at roughly 13-month intervals, when Earth catches up to Saturn in its faster orbit and aligns properly for a gravity-assisted trajectory. Outside these windows, missions are still possible but require substantially more fuel. The structure of the solar system also means something else. There is a categorical jump beyond Mars. Everything within Mars's orbit is part of the inner solar system, with relatively short distances and relatively short mission times. Everything beyond Mars is the outer solar system, with distances measured in billions of kilometers and mission times measured in years or decades. The asteroid belt is not just a region of debris. It is, in a real sense, the boundary between two categorically different parts of our solar system. Crude missions, when they happen, will follow the same logic. The inner solar system will be visited first. Mars will be reached, probably within the next few decades. The technology and experience developed there will, eventually, enable consideration of missions further out. But the jump from Mars to Saturn is not a small step. It is a categorical change in mission architecture. A Mars mission, in current planning, takes about 2.5 years total, 9 months out, 500 days on the surface, 9 months back. A Saturn mission, even using the best gravity assist trajectories and the most efficient propulsion currently feasible, would take 7 years one way at minimum. Add a mandatory waiting period for return alignment, and the total mission duration grows to 14 years or more. 2.5 years versus 14 years, the same physics but on a different scale. Saturn, in this sense, is at the edge of what is even theoretically discussable for human missions in the next several decades. Anything beyond Saturn falls into a category that is, with current technology, simply outside the conversation. Uranus and Neptune are not destinations for human exploration. They are destinations for robotic probes, and even those are rare. Voyager 2 remains the only spacecraft to have flown past both planets, and it did so in 1986 and 1989. We have not been back. Saturn, then, is the practical limit of human reachability in the near term. And as the rest of the conversation will show, even that limit is more of an asymptote than a destination, approachable in principle, practically never closed. When Cassini was operating in orbit around Saturn, the engineers in Pasadena had a particular relationship with the spacecraft. They sent commands. The commands took roughly 80 minutes to arrive. The spacecraft executed the commands and sent back data. The data took another 80 minutes to return. A single back-and-forth communication from command to confirmation took about 2 hours and 40 minutes. This is what light speed delay means at the distance of Saturn. The number varies. During Cassini's tour of Saturn, the one-way light travel time ranged from 67 minutes when Earth and Saturn were closest, to 85 minutes when they were farthest, on average around 80 minutes. The round-trip delay, the time required for any exchange, varied accordingly from about 2¼ hours to nearly 3 hours. To put this in perspective, consider how communication delays scale with distance. The Moon is 1.3 light seconds from Earth. When Apollo astronauts were on the lunar surface, their conversations with Houston had a noticeable but workable delay, about 1½ seconds for a question and an answer to complete a round trip. The pauses were perceptible. The Apollo 11 transcripts show the slight rhythm of waiting between exchanges. Mars is between 3 and 22 minutes light time from Earth, depending on relative positions. Communication with a Mars rover is asynchronous. You send a command. Hours later, you find out whether it worked. Mission controllers for Curiosity, Perseverance, and the Mars helicopters have adapted to this. Plans are made days in advance. Real-time response to unexpected events is impossible. Saturn is 80 minutes one way on average. The asynchronicity at Mars becomes something stranger at Saturn, not just delayed conversation. Effectively, no conversation at all. For Cassini, this meant that mission planning had to be entirely pre-scheduled. Engineers built command sequences that would execute over hours or days, with the spacecraft following the plan autonomously. When something unexpected happened, by the time the engineers learned about it, the situation had often resolved itself one way or another. The spacecraft had to handle most events on its own, using onboard logic to respond to common issues. For a hypothetical crewed mission, this would mean something even more profound. Imagine a crew member on a spacecraft orbiting Saturn. They develop a medical issue. They radio Earth for advice. Their message takes 80 minutes to arrive. Mission Control receives it, consults specialists, formulates a response, and transmits the answer. The crew member receives that answer 80 minutes after Mission Control sent it. Total elapsed time, roughly 2 hours and 40 minutes. For a slow-developing medical issue, this might be workable. For on acute emergency, it is not help at all. The crew must, in any urgent situation, function as their own physicians, their own engineers, their own decision-makers, their own everything. Earth is a resource, but only for non-urgent matters. This is fundamentally different from anything humans have ever experienced. Even Antarctic research stations, when they are at their most isolated, have communication delays measured in fractions of a second. Submarine crews have similar near-instantaneous communication with their command. Even ISS astronauts in low Earth orbit talk to ground controllers with almost no delay. A Saturn crew would be, in the moment of any actual emergency, alone, not figuratively, literally. The fastest possible message to Earth and back would take longer than most acute emergencies allow. There is one more dimension worth noting. The light delay is the floor, the minimum delay imposed by physics. Actual operational delays are usually longer. Signal processing time, the need for human review of received messages, time zone differences between sender and receiver, all add to the total. A practical round-trip Cassini communication often took the better part of a working day, not the strict 2-5 hours that physics allows. For Cassini, this was a known constraint that the engineers built around. For a human crew, the constraint becomes a defining feature of daily life. 80 minutes to receive a response to any question. 80 more for any clarification. The pace of communication slows to something humans have never experienced as a way of life. That is the delay. Now consider what carries the message across the delay. The Cassini spacecraft, the launched on October 15, 1997. It arrived at Saturn on July 1, 2004. The journey took 6 years, 8 months, and 16 days. This is, by spaceflight standards, a normal duration for a Saturn mission. Cassini was not slow. It used the most efficient trajectory available to it at the time, leveraging multiple gravity assists from inner planets to build up the velocity needed to reach the outer solar system. The duration is not a flaw in the mission. It is what reaching Saturn actually takes with chemical rockets and gravity assist trajectories. To understand why it takes so long, consider the alternative. A direct flight from Earth to Saturn without gravity assists would require an enormous amount of fuel. The spacecraft would need to escape Earth's gravity, achieve a velocity high enough to reach Saturn's orbit directly, and then have enough fuel left to slow down once arriving. The Tsiolkovsky rocket equation, which governs the relationship between fuel and velocity in rocketry, makes this prohibitive. The amount of fuel required for a direct flight would be so large that the spacecraft itself would be mostly fuel tank, with minimal capacity for instruments or other useful equipment. Gravity assists work around this. By passing close to a planet at the right angle and speed, a spacecraft can pick up some of the planet's orbital momentum without using its own fuel. The planet barely notices, but the spacecraft gains a significant boost. By chaining these assists across multiple planets, you can build up the velocity needed for outer solar system missions without carrying impossible amounts of fuel. Cassini's path used 4 planetary gravity assists: Venus twice, Earth once, Jupiter once, Jupiter once, Jupiter once, Jupiter once. Jupiter. The Venus flybys in April 1998 and June 1999 were each used to boost Cassini's velocity for the next leg of the journey. The Earth flyby in August 1999 provided a final inner planet boost of 55 kilometers per second. The Jupiter flyby in December 2000 was the last and largest of the assists, using Jupiter's massive gravity to fling Cassini outward into the orbit that would eventually intersect Saturn's. This is what reaching Saturn requires, not a straight line, a careful choreography across multiple planets, timed to use their orbital positions to advantage. Cassini's specific trajectory is called a Venus-Venus-Earth-Jupiter gravity assist, abbreviated VVAJ. The acronym describes a tour of the inner solar system that took years to complete, with the goal of building up enough velocity, slowly and incrementally, to eventually reach Saturn. Voyager 1 reached Saturn in 3 years and 2 months, faster than Cassini. But Voyager was a flyby mission, not an orbital one. It did not need to slow down at Saturn. It used the different gravity assist sequence, including a much closer approach to Jupiter that provided more momentum but also higher radiation exposure for the spacecraft. For an orbital mission which has to decelerate to be captured by Saturn's gravity, Voyager's approach would not work. Cassini's slower, more elaborate path was necessary because it had to arrive at exactly the right velocity to enter Saturn's orbit. For a human mission, the journey duration becomes a fundamental constraint. 7 years one way is not a duration that any current human spaceflight architecture is designed around. The longest continuous human stay in space is roughly 437 days, set by cosmonaut Valery Polyakov aboard Mir in the 1990s. 7 years is more than 5 times that duration. And it is only the outbound leg. A return trip to Saturn would require another 7 years on the way back, assuming similar gravity assist trajectories were available. In practice, the return trip might take longer, because the launch windows from Saturn back to Earth do not align with the original outbound trajectory's geometry. The crew might wait years at Saturn for the right return window. The total mission duration, including travel and waiting time, would likely be in the range of 14 to 18 years. 14 to 18 years. Outside of Earth. With everything that implies biologically, psychologically, and operationally, and the only way to make even the outbound journey possible is to spend years borrowing energy from planets that have no idea they are participating in the mission. The next part of the story is about how that borrowing works. In 1961, a graduate student named Michael Minovich, working at NASA's Jet Propulsion Laboratory, made a calculation that changed how interplanetary missions are designed. Minovich was studying the three-body problem in celestial mechanics, a notoriously difficult problem in physics involving the motion of 3 gravitationally interacting bodies. As part of his work, he calculated what would happen to a spacecraft passing close to a planet during interplanetary travel. The math showed something remarkable. A spacecraft, by approaching a planet at the correct angle, could effectively borrow momentum from that planet. The planet's gravity would deflect the spacecraft's path, and in the process, The spacecraft would emerge from the encounter moving faster relative to the Sun than it had been before. This was the gravity assist, and it would later become the foundation of essentially every outer solar system mission ever conducted. The mechanism is more subtle than it first appears. The planet itself, in its orbit around the Sun, has enormous momentum. The spacecraft, much smaller, has comparatively little. When the spacecraft passes close to the planet, gravity pulls them toward each other. In the reference frame of the planet, the spacecraft is gaining and then losing speed symmetrically, ending up with the same velocity relative to the planet that it entered with, just in a different direction. But in the reference frame of the Sun, which is what matters for interplanetary travel, the geometry produces an asymmetric result. The spacecraft picks up some of the planet's orbital momentum and emerges with a different, generally higher velocity relative to the Sun. The planet, technically, loses an equivalent amount of momentum, but because the planet's mass is so much larger than the spacecraft's, the effect on the planet is unmeasurably small. The spacecraft gains kilometers per second. The planet loses something on the order of millionths of a millimeter per year in its orbital speed. For Cassini, the gravity assists were essential. The spacecraft launched with enough fuel to escape Earth's gravity and begin its interplanetary trajectory, but nowhere near enough to reach Saturn directly. Without assists, Cassini would have been a much shorter mission, perhaps reaching the asteroid belt before running out of usable trajectory. The first Venus flyby, in April 1998, was the initial boost. Cassini swung within 284 kilometers of Venus's surface, deflecting its trajectory and gaining velocity. The spacecraft then looped back through the inner solar system. A second Venus flyby in June 1999 provided another boost, this time within 600 kilometers of the surface. Then Earth in August 1999, with Cassini passing 1,171 kilometers above Earth, the closest of any of its assists. The Earth flyby added 55 kilometers per second to Cassini's velocity, a significant boost. The final assist was Jupiter in December 2000 at 10 million kilometers from the giant planet, far enough to avoid the worst of Jupiter's radiation environment while still gaining substantial momentum. The combined effect of these four assists added approximately 20 kilometers per second to Cassini's velocity, the difference between a spacecraft that could not reach Saturn at all and one that could. This boost was provided by the planets, free of charge, in exchange for negligible amounts of their orbital momentum. The same approach would be required for any human mission to Saturn. Direct flights with chemical propulsion are not feasible at any practical scale. Even with the most powerful rockets currently designed, the fuel mass required for a direct Saturn flight would dwarf the spacecraft itself. Gravity assists are not just preferred, they are required. But there is a catch when humans are involved. Gravity assist trajectories are slow because they require waiting for the planets to be in the right positions. Cassini's 7-year journey reflects this. A more direct trajectory, using nuclear propulsion or some future advanced propulsion system, might cut the time substantially. But until such systems are developed and proven, gravity assists are the only path forward, and that path takes 7 years. This is the same constraint that the Mars sample return mission faced, that the Mars human mission faces, and that any Saturn human mission will face. Cheap fuel is not available. The energy has to come from somewhere. The somewhere is the planets we pass on the way, contributing tiny fractions of their orbital momentum to the spacecraft as it makes its slow way outward. And while the spacecraft is making that slow way outward, it is exposed for the entire 7-year duration to everything that the universe does to objects passing through deep space. Between Earth and Saturn there is approximately 1 Points Kropler, 43 billion kilometers of essentially empty space. Not completely empty. There are charged particles streaming from the Sun called the solar wind. There are interplanetary magnetic fields. There are occasional cosmic ray bursts from distant astrophysical events. There are tiny dust grains, mostly debris from collisions in the asteroid belt or from comets. And there is the cold of deep space, where temperatures drop to a few degrees above absolute zero in any region not warmed by direct sunlight. A spacecraft crossing this region for 7 years has to survive all of it. The Voyager spacecraft, launched in 1977, demonstrated what survival in deep space looks like over even longer durations. Both Voyagers passed Saturn in 1981 before continuing onward, eventually crossing into interstellar space. They are still operating, almost 50 years after launch, with degraded but functional systems. They have survived the cumulative effects of nearly 5 decades of cosmic radiation, micrometeorite impacts, thermal cycling, and the slow aging of every component. This survival is not automatic. It requires specific engineering choices, many of which are not available for crewed missions. The Voyager spacecraft are powered by radioisotope thermoelectric generators, RTGs. These are devices that produce electricity from the heat generated by the radioactive decay of plutonium-238. The plutonium is sealed inside heavily shielded modules. The heat from its decay is converted to electricity by thermocouples, and the resulting power output is steady and reliable for decades. The Voyagers each launched with about 470 watts of electrical power. After nearly 50 years of operation, each is producing approximately 230 watts. Slow, predictable, irreversible decay. Cassini also used RTGs, with 3 units providing a combined 885 watts at launch. By the end of the mission in 2017, the output had degraded to about 633 watts, an expected loss but a substantial one. The same plutonium decay process powered the spacecraft for its entire mission duration. Without RTGs, neither Voyager nor Cassini would have functioned in the outer solar system, because solar panels at Saturn's distance produce only a small fraction of what they produce at Earth, far too little to power a spacecraft of any meaningful complexity. For a crewed mission, the power problem becomes even more severe. A crew of 4 or 6 humans requires substantially more power than a robotic probe. Life support alone, including air filtration, water recycling, temperature regulation, and equipment operation, demands kilowatts of continuous power. Adding scientific instruments, communication systems, computers, and propulsion systems pushes the requirement into the range of tens or hundreds of kilowatts. Solar power at Saturn's distance cannot supply this. RTGs cannot either, at any reasonable scale. The only practical option for crewed outer solar system missions is a small nuclear reactor, similar to those used in submarines and aircraft carriers, scaled down for spacecraft use. These reactors do not exist for spaceflight. Various designs have been studied, including some active programs in the 2020s for fission surface power systems intended for Mars and Moon missions. None has been flight qualified for use beyond Mars. A reactor capable of powering a crewed Saturn mission for 20 years would require a development program of substantial scope, with no current funding or schedule. The cold of deep space is another challenge. Equipment exposed to the cold of interplanetary space, far from the Sun, needs constant heating to remain operational. Cassini used part of the RTG heat for this purpose, channeling waste heat from the generators into the spacecraft's interior to keep electronics warm. The thermal management of a crewed spacecraft over 7 years of cruise to Saturn would be substantially more complex because the crew compartment itself must be maintained at a temperature humans can tolerate, while the surrounding environment is hundreds of degrees colder. Radiation, in the form of galactic cosmic rays and solar particle events, gradually degrades electronics. Components fail. Memory bits flip. Computers crash. Every component on a spacecraft is selected and tested for its radiation tolerance, and even the best components have limited lifetimes in the radiation environment of deep space. For Cassini, the engineers expected component failures and built-in redundancy. The spacecraft had 2 of every critical system, and it relied on backup components multiple times during its mission to continue functioning. For a crewed mission, redundancy becomes both more critical and more difficult, because the systems involved are larger and more complex. By the time a Saturn-bound spacecraft arrives, after 7 years of exposure to all of these effects, it has aged. Some of its components have failed. Others are degraded. The crew, if there is one, has aged biologically in ways we will discuss later, and the destination, finally, is in view. That destination, however, is not what most people imagine when they think of a planet. On July 1, 2004, After nearly 7 years of travel, Cassini reached Saturn. The arrival was not a smooth coast into orbit. It required a precisely timed engine burn that lasted 96 minutes, during which the spacecraft's main engine fired continuously to slow it down enough for Saturn's gravity to capture it. The burn reduced Cassini's velocity by 6,226 meters per second, just barely enough to enter an orbit. Too short, and the spacecraft would have flown past Saturn into deep space, unable to return. Too long, and it would have crashed into the planet or one of its rings. The burn worked. Cassini entered an elliptical orbit around Saturn, with the closest point about 19,980 kilometers from the planet's cloud tops. The spacecraft, now bound to Saturn's gravity, began its 13-year tour. But the question that mission planners had been grappling with from the beginning was about to become acute. The question was, how does one explore Saturn? For inner solar system bodies, the answer is straightforward. You land. The Moon, Mars, Venus, even small asteroids have all received landers. They have solid surfaces. You can put a spacecraft on them. You can drive a rover across them. You can dig into them. The basic mode of planetary exploration since the 1960s has been to put something on the surface and operate it there. Saturn does not work like this. Saturn has no surface. This is not a metaphor. Saturn is composed primarily of hydrogen and helium, with smaller amounts of methane, ammonia, water, and various other compounds. The outer layers are gaseous, becoming denser as you descend. The atmospheric structure is not what most people mean when they say atmosphere. It is essentially the entire planet. There is no point at which you can say, below this is the planet, above this is the atmosphere. The planet is the atmosphere, all the way down. If you somehow descended into Saturn with a spacecraft capable of surviving the pressure, you would not find a hard surface to land on. You would find gas getting denser. At some depth, the gas would become so compressed that it would behave like a liquid. Below that, the liquid would become so compressed that it would take on properties of a metal. At the very center, models suggest there is a dense core, perhaps rocky, perhaps a metallic hydrogen and rock mixture. But the nature of this core is still debated. There is no surface. There is only continuous gradient from outer atmosphere through liquid layers to whatever lies at the center, with no clear boundary anywhere. For exploration, this changes everything. You cannot land on Saturn. You can fly through its upper atmosphere briefly, as Cassini did on its final plunge, but you cannot remain at any altitude indefinitely. The atmosphere is too dense at lower altitudes to support orbit, and not dense enough at high altitudes to support flight. There is no stable place to be at Saturn except in orbit around it, well outside the atmosphere itself. This is a peculiar engineering reality. We have spent decades sending spacecraft to other planets and moons and developing the tools to explore them at the surface. None of those tools applies to Saturn. The instruments that work on Mars, the rovers, the landers, the drills, are useless at Saturn because there is nothing for them to land on. The instruments that work in orbit, the cameras, the spectrometers, the radio occultation experiments, are the only ones that apply. Cassini's entire mission, throughout its 13 years at Saturn, was an orbital mission. It never landed on Saturn because landing on Saturn is impossible. The only landing achieved by the Cassini-Huygens mission was on Titan, Saturn's largest moon. The orbiter itself, throughout its time in the Saturn system, remained in orbit, observing the planet, the rings, and the moons from various distances. For human exploration, the implication is profound. The traditional model of planetary exploration, which involves landing humans on the surface, planting flags, taking samples, and conducting research from a base camp, does not apply to Saturn. There is no surface to land on. There is no base camps to establish. There is, in the most literal sense, nowhere to be at Saturn except in orbit around it. And this is the strangest engineering problem in spaceflight. The destination of a Saturn mission is not really a destination at all. It is more like an environment to visit, briefly, from a safe orbital distance, with no possibility of staying. This is the first of the major inversions that the title of tonight's conversation is hiding. We tend to think of going to a planet as a process of arriving at a place. At Saturn, there is no place to arrive at. The journey ends in something more like orbital observation than in any meaningful sense of presence on the planet itself, and the reason for this, when you understand the physics, is more complete than it first appears. Saturn has approximately 95 times the mass of Earth. This is a number that does some unexpected work. With 95 Earth masses, you might expect Saturn to be a very heavy, very dense object. But Saturn's density, calculated from its mass and its volume, comes out to about 0.687 grams per cubic centimetre. This is less than the density of water. Saturn, if you could find a bathtub large enough, would float. The reason is its composition. Saturn is roughly 75% hydrogen, 25% helium, and small amounts of heavier elements. Hydrogen and helium are the two lightest elements in the periodic table. A planet made primarily of them, even at the scale of Saturn, has a remarkably low overall density. Saturn is large because it has accumulated enormous amounts of these light gases through gravity over the age of the solar system. It is not dense in the way Earth is dense, but as you descend into Saturn's atmosphere, the density increases rapidly. The gas at the top is thin, similar to the air on Earth at a few times atmospheric pressure. A few hundred kilometers down, the pressure has increased to where the gas behaves more like a liquid. A few thousand kilometers down, the pressure is enormous, and the hydrogen has been compressed into something called liquid metallic hydrogen, a state in which the molecules of hydrogen are pressed so close together that electrons begin to roam freely between atoms, giving the substance metallic properties. This is not a state of hydrogen we have ever produced in any laboratory on Earth at scale, and it makes up the bulk of Saturn's interior. The pressure at these depths is extreme. At depths of about 20,000 kilometers into the planet, pressures reach roughly 2 million Earth atmospheres. At the deeper levels, pressures continue to climb to many millions of atmospheres. These are pressures so high that no spacecraft has ever been designed to operate in them, and no plausible spacecraft could. For comparison, the Titanic submersible, which famously imploded at depth in 2023, was operating at a pressure of about 380 atmospheres. The deepest part of Earth's oceans, the Mariana Trench at about 11,000 meters, has a pressure of about 1,100 atmospheres. Saturn's deep interior reaches pressures thousands of times higher than the deepest ocean. There is no material we know how to engineer that can withstand these conditions. This is what no surface means at Saturn. It is not that the surface is hard to find. It is that there is no boundary at all. Just continuous gradient from manageable atmospheric pressure at the Kyle tops, through dense gas, through liquid metallic hydrogen, to whatever lies at the planet's core. At every depth the pressure is rising. At no depth is there a stable place to stand. For a probe to land on Saturn would require it to descend to some depth and then stop. There is no depth at which it can stop. As it descends, it sinks deeper. The pressure crushes it further, until at some point it is compressed beyond any structural integrity ahead. The probe becomes part of the atmosphere. It dissolves into the surrounding fluid. It is consumed by the planet, not landed on it. Cassini's final plunge on September 15, 2017, was a deliberate execution of this process. The spacecraft entered Saturn's upper atmosphere at high speed. The drag began to slow it. The atmospheric pressure began to crush it. The spacecraft tumbled, lost orientation, and as it descended into denser layers, it began to disintegrate. By the time it was a few hundred kilometers below the cloud tops, Cassini was gone. The pieces continued to fall, breaking apart further, eventually being incorporated into the gas of Saturn itself. There is, in a literal sense, no trace of Cassini left as a recognizable object. It is now part of Saturn. This is what visiting Saturn means at the physical level. The planet does not host visitors. It absorbs them. For human exploration, this changes the fundamental nature of the mission. Humans cannot stand on Saturn. They cannot live on Saturn. They cannot live on Saturn. They cannot land on Saturn even briefly. The only relationship a human spacecraft can have with Saturn is to remain in orbit, observe the planet from a safe distance, and never approach the atmosphere except to be destroyed. The conversation, at this point, has to pivot. If Saturn itself is not the destination, then what is? The answer, when serious people discuss Saturn missions, is the moons. Saturn has 146 known moons as of 2024, ranging from small irregular bodies a few kilometers across to Titan, larger than the planet Mercury. Some of these moons are nothing more than captured asteroids. Others have characteristics that make them genuinely interesting as scientific destinations, possibly even as places where signs of life could be searched for. 2 moons in particular have emerged as the primary candidates, and both of them, like Saturn itself, have a particular set of problems that the question of human visitation runs directly into. Before moving to the moons, it is worth sitting briefly with what crushing pressure means at Saturn, because this is the kind of detail that gets repeated in popular accounts without ever being made concrete. Earth's atmospheric pressure at sea level is 1 atmosphere. This is the baseline. Every other pressure can be measured in relation to it. In a passenger aircraft flying at cruising altitude, the cabin is pressurized to roughly 0.75 atmospheres, slightly thinner than ground-level air, enough that some passengers notice slight ear discomfort during ascent and descent. In a typical scuba diver's tank, the gas is compressed to approximately 200 atmospheres. The tank walls have to be substantial to contain this pressure safely. In the deepest reaches of the ocean, the Mariana Trench, water pressure reaches about 1,100 atmospheres. This is enough to crush any unprotected human body instantly. Submarines built to reach these depths, like the Trieste in 1960 or the Limiting Factor in 2019, use spherical pressure hulls made of very thick titanium or other materials chosen specifically for resistance to this kind of pressure. In Saturn's atmosphere, at a depth of approximately 1,000 kilometers below the cloud tops, the pressure is approximately 1 atmosphere, similar to Earth's surface. This is the only depth in Saturn that resembles anything Earth-like, and even at that depth, the temperature has risen to a few hundred degrees Celsius, well beyond what humans or most materials can tolerate. Continue descending. At 10,000 kilometers below the cloud tops, the pressure is in the range of 1,000 atmospheres, similar to the Mariana Trench. Submarine-grade materials might survive briefly here, but the temperatures are climbing past 5,000 degrees Celsius. Nothing made of ordinary matter would last long. At 30,000 kilometers below the cloud tops, the pressure reaches approximately 2 million atmospheres. Temperatures exceed 10,000 degrees. This is where liquid metallic hydrogen begins to form. No material engineered by humans can survive these conditions for any meaningful duration. The center of Saturn, perhaps another 30,000 kilometers below this, sits at pressures and temperatures that we can only model, never reproduce. The pressure is on the order of tens of millions of atmospheres. The temperature is similar to or higher than the surface of the Sun. This is what Cassini fell into during its final descent. The spacecraft, designed to operate in orbit in the relative vacuum of space, had no chance against these conditions. Within minutes of entering the upper atmosphere, the spacecraft began breaking up. The drag on its solar array-sized appendages was the first problem. The increasing pressure was the second. The rising temperature was the third. By the time Cassini was 1,000 kilometers below where it first encountered significant atmosphere, it was already disintegrated into separate pieces, themselves breaking apart further, eventually disappearing into the gas of the planet. For any future mission to Saturn, even a robotic one designed specifically for atmospheric study, the depth limit is small. The Galileo probe at Jupiter dropped into that planet's atmosphere in 1995, survived to a depth of about 150 kilometers below the cloud tops, reaching about 22 atmospheres of pressure before being destroyed by heat and pressure. A similar probe at Saturn would have a similar limit. A few hundred kilometers of useful descent, then destruction. This is the practical meaning of having no surface. The planet does not just lack a place to stand, it actively destroys anything that tries to find one. The destruction begins gently at the cloud tops and becomes complete within a few hundred kilometers of penetration. Below that, nothing engineered by humans has any business being, so the moons become the destination by default, not because they are the most interesting parts of the Saturn system, although several of them are extraordinarily interesting, but because they are the only parts that can be landed on, walked on, or studied from the surface. Without the moons, a mission to Saturn would be limited to orbital observation and atmospheric probes. With the moons, the mission can become something more. The moons, however, are not Saturn. They are bodies in their own right with their own challenges. Going to them requires solving an entirely different set of problems, and those problems form the next layer of why returning from Saturn is essentially impossible. When mission planners actually sit down to consider what a Saturn mission would look like, the conversation pivots almost immediately from Saturn to its moons. This pivot is unusual in planetary exploration. For Mars, the planet itself is the target. For Mercury, the planet is the target. For Venus, the same. The moons of these inner planets are minor objects, scientifically interesting but not the primary destinations of major missions. The planets are where the action is. At Saturn, the situation reverses. Saturn itself is the most magnificent target of the outer solar system, with its rings, its atmospheric weather, its powerful magnetic field. But it is also the part of the system that cannot be landed on, cannot be touched, cannot be physically reached except by destruction. The moons, by contrast, can be landed on. They can be walked across, drilled into, sampled. They can host instruments that work for years or decades. For any mission that wants to do more than fly past Saturn in orbit, the moons are where the meaningful exploration happens. Saturn has 146 known moons as of recent counts in 2024. Most of them are small, irregular bodies, captured asteroids or fragments from collisions, ranging from a few kilometers to a few hundred kilometers across. They have no atmosphere, no surface activity, and no resources that would justify a dedicated mission. They are interesting to planetary scientists, but not destinations for major exploration. 7 of Saturn's moons are large enough to be roughly spherical, held together by their own gravity. Titan, Rhea, Iapetus, Dione, Tethys, Enceladus, and Mimas. These are the moons that get serious scientific attention. Each has its own history, its own surface features, its own composition. Cassini studied them all during its 13 years in the Saturn system, mapping their surfaces, measuring their compositions, and identifying which ones might harbour conditions of astrobiological interest. 2 moons stand out from the rest: Titan and Enceladus. Titan is by far the largest of Saturn's moons, at 5,150 kilometers in diameter, larger than the planet Mercury. It has a thick atmosphere, the only moon in the solar system that does. It has rain. It has lakes and rivers on its surface, although the rain and the rivers are made of liquid methane and ethane rather than water. It is the only world in our solar system, besides Earth, where stable surface liquids exist. Enceladus is much smaller, only about 500 kilometers in diameter, but it is one of the most surprising bodies in the solar system. Cassini discovered that geysers erupt from its south polar region, sending plumes of water vapor and ice particles into space. The geysers are powered by a subsurface ocean of liquid water, kept warm by tidal heating from Saturn's gravity. Inside Enceladus, beneath an ice shell several kilometers thick, there is a global ocean of salty liquid water in contact with rocky sea floor, exhibiting conditions that astrobiologists consider potentially habitable. These 2 moons are why anyone talks seriously about going to Saturn at all. Without them, Saturn would be a destination of scientific interest but limited operational scope. With them, Saturn becomes a system that includes potentially habitable environments, which gives any mission a target. The next several sections walk through what we know about these moons, what reaching them requires, and why even reaching them does not solve the return problem. We start with Titan. Titan was discovered in 1655 by the Dutch astronomer Christian Huygens, using a telescope he had built himself. For most of the centuries after its discovery, Titan remained a mystery. Even with the best Earth-based telescopes, the surface was hidden by a thick, hazy atmosphere. Astronomers knew it was large, that it had clouds, that it was the second largest moon in the solar system after Ganymede, but what lay beneath the haze was unknown. The first close look came from Pioneer 11 and the 2 Voyager spacecraft in the late 1970s and early 1980s. They confirmed that Titan had a substantial atmosphere, primarily nitrogen, with significant methane. But they could not see the surface. The haze, made of complex organic compounds called tholins, was opaque to visible light. It was Cassini, arriving in 2004, and its companion the Huygens probe that finally revealed Titan in detail. Cassini carried radar instruments that could see through the haze, mapping the surface in detail. Huygens, after separating from Cassini in December 2004, descended through the atmosphere and landed on the surface on January 14, 2005, the first and so far only landing on any world in the outer solar system. What Cassini and Huygens revealed was a place stranger and more familiar than anyone had quite anticipated. Titan is 5,150 kilometers in diameter, larger than Mercury, almost as large as Mars. Its atmosphere extends about 600 kilometers above the surface, far thicker than Earth's. At the surface, the atmospheric pressure is approximately 1.45 atmospheres, slightly higher than Earth's surface pressure. The atmosphere is 95% nitrogen, with small amounts of methane, hydrogen, and other compounds. In overall composition, Titan's atmosphere bears a striking resemblance to early Earth's before life filled it with oxygen. The surface, at 178 degrees below 0 Celsius, is far colder than anywhere on Earth. At that temperature, water is rock hard. Ice is the primary surface material across much of Titan. Mountains made of water ice, canyons cut into water ice, plains of water ice covered in organic dust. But methane, which is a gas at Earth temperatures, is a liquid at Titan's temperatures. Titan has methane lakes, methane rivers, methane rain. The atmospheric cycle on Titan resembles Earth's water cycle in form, with evaporation from lakes, cloud formation, precipitation, and runoff back into low areas. The substance involved is different. The structure is remarkably similar. The largest lake on Titan is called Kraken Mare. It is about 400,000 square kilometers in area, comparable to the Caspian Sea on Earth. There are dozens of smaller lakes and seas. There are river channels that have clearly carried liquid for long periods of geological time. There is evidence of seasonal weather, although Titan's seasons each last about 7 Earth years because of the long orbital period. For exploration, Titan presents a strange combination of features. The thick atmosphere makes flight possible in a way that the thin atmosphere of Mars does not allow. NASA's Dragonfly mission, scheduled for launch in 2027 and arrival in 2034, is a small nuclear-powered helicopter designed to fly through Titan's atmosphere, hopping from location to study the surface chemistry. The same atmospheric density that makes Titan unique also makes it the only outer solar system moon where rotorcraft flight is straightforward, but the cold, the lack of oxygen, the methane chemistry, and the immense distance from Earth combine to make Titan a place that is, despite its surface familiarity, profoundly inhospitable to humans. Walking on Titan would not require a pressurized suit, because the atmospheric pressure is comfortable, but it would require extreme cold weather gear and a self-contained breathing system. The temperature would freeze a human body in minutes. The methane atmosphere would not support respiration, and reaching Titan for any human mission requires first reaching Saturn, which we have already established takes 7 years minimum, and then descending into Titan's atmosphere and landing, which requires its own dedicated lander vehicle, and then doing the entire process in reverse if anyone is to return. Each step adds time. Each step adds mass. Each step adds mass. Each step adds points of failure. From a distance, Titan looks like the kind of place where a science fiction writer might set a story. It has an atmosphere. It has weather. It has lakes and rivers. It has clouds. It has rainfall. It has stable surface liquids. By the standards of the outer solar system, Titan is shockingly Earth-like. None of the other moons of Saturn have anything resembling these features. Most have no atmosphere at all, with surfaces exposed directly to space. But every Earth-like feature of Titan is, on closer inspection, dangerous in a specific way. The atmosphere looks right. It is dense enough to walk through without a pressure suit. It is thick enough to support flight, even at low altitudes. It has the right approximate density to feel familiar to a human standing on the surface, but it contains essentially no oxygen. The 95% nitrogen is unbreathable on its own. The small amounts of methane and hydrogen do not support human respiration. A human standing on Titan without a breathing apparatus would lose consciousness within seconds. just as if standing in a sealed room with nitrogen but no oxygen. The lakes look right. They have shorelines, they have islands, they have tides driven by Saturn's gravitational pull on Titan's orbit. From orbit, in radar images, the lakes look like ordinary terrestrial bodies of water. But they are not water. They are liquid methane and ethane, hydrocarbons that are gases on Earth but liquids at Titan's extreme cold. The chemistry of the lakes is alien. The dynamics are different from water. The interactions with the surface are different. The temperature is far below freezing for any familiar substance. The rain looks right. It falls from clouds. It runs in channels across the surface. It carves valleys into the ice landscape. But again, the rain is not water. It is methane, falling at temperatures cold enough to freeze a human instantly. A drop of Titan rain landing on bare human skin would cause immediate frostbite and tissue damage. The temperature is the most fundamental problem. Titan's surface temperature averages around minus 179 degrees Celsius. This is colder than any natural environment on Earth. Earth's coldest recorded surface temperature is about minus 89 Celsius in Antarctica. Titan is more than twice that cold. At this temperature, ordinary materials become brittle. Steel cracks. Rubber shatters. Metals lose their elasticity. Plastics fail. Engineering on Titan requires materials specifically designed for cryogenic temperatures, materials that retain useful properties at temperatures close to absolute zero. For human exploration, the implications are severe. A spacesuit for Titan cannot simply be a heated suit, because the surrounding temperature is so far below freezing that ordinary insulation does not work. The suit must be actively heated, drawing significant power, and the heating systems must work continuously for the entire duration of any surface activity. A power failure on the surface of Titan would mean rapid freezing of any crew member exposed to the environment. The atmosphere also presents fire hazards. Methane is flammable. If a small amount of oxygen leaked from a human habitat into the methane-rich atmosphere, it would combine with the methane and could ignite. Engineering for Titan habitats would have to be careful about preventing such leaks, because any combustion event on Titan would have explosive potential. The Huygens probe, which landed in January 2005, demonstrated the practical difficulties. Huygens was designed to descend through Titan's atmosphere, take measurements, and operate on the surface for as long as its batteries held. The probe successfully reached the surface and operated for about 90 minutes before transmission was lost. During its descent, the probe carefully measured atmospheric composition, temperature, pressure, and wind speeds at different altitudes. It took photographs of the surface, showing what looked like a frozen riverbed strewn with rounded ice pebbles, the result of geological processes involving liquid methane rather than water. After 90 minutes on the surface, the probe stopped transmitting. The cold drained its batteries faster than predicted. The probe was not designed for long-term operation. It was designed for one descent, one brief surface phase, and then the end. Huygens is the closest any human-built object has come to demonstrating what a longer mission might look like. 90 minutes. After that, the cold won. Future missions, including Dragonfly, are designed with nuclear power specifically to address this. Solar power is insufficient at Titan because of the thick atmosphere and the distance from the sun. Battery power is insufficient because of the rate of energy lost to the environment. Only continuous nuclear power, in the form of radioisotope thermoelectric generators or, in larger missions, small reactors, can sustain extended operations at Titan. This is what Earth-like actually means at Titan. Familiar features, fundamentally hostile chemistry. A surface you could land on, but not survive on, without continuous power and constant attention to the environment. A planet that, looked at from above, suggests possibility, and that, examined closely, reveals the same hard constraints that the rest of the outer solar system imposes. On January 14, 2005, after a 3-week separation from Cassini and a parachute descent through Titan's atmosphere, the Huygens probe touched down on Titan's surface. The descent took 2 hours and 27 minutes. During that descent, Huygens collected measurements that completely changed our understanding of Titan. It mapped the atmospheric composition at different altitudes. It measured wind speeds and atmospheric structure. It took 700 photographs of the descent, showing the haze giving way to the surface. river channels emerging into view, and finally the landing site itself. The landing was soft. Huygens hit the surface at about 4.5 meters per second, the equivalent of dropping it from a height of about 1-2 meters on Earth. The surface was firm, like ice covered with a layer of softer material that some scientists liken to wet sand. The probe came to rest. Its instruments began collecting data on the surface itself. The first surface photograph showed rounded pebbles, smooth, ice-like stones the size of large rocks scattered across a flat plain. The pebbles had clearly been transported and shaped by some kind of fluid flow. The riverbed interpretation was inescapable. Liquid had carried these pebbles, smoothed them, deposited them at the location where Huygens landed. The fluid was almost certainly methane. Huygens continued transmitting for about 90 minutes after touchdown. During that time it sent back surface temperature, atmospheric composition, wind speeds at the surface, and additional photographs. Then the battery, which had been operating in the extreme cold, drained faster than mission planners had hoped. The transmissions weakened. The signals stopped. Cassini, which had been receiving the data and relaying it to Earth, made one final pass to confirm there were no further signals from Huygens. There were none. The probe had completed its mission. It is still on Titan, presumably frozen and silent, at the location where it landed in January 2005. Huygens accomplished several historical firsts. It was the first spacecraft to land on a world in the outer solar system. It is still, 20 years later, the only spacecraft to have landed there. It returned the first detailed measurements of Titan's atmosphere and surface. It demonstrated that Titan has stable surface liquids and active geological processes. It opened a research program that continues today. It also demonstrated the difficulty of operating in the outer solar system. 90 minutes of surface operation after a 7-year cruise on a probe that was designed for exactly this kind of brief atmospheric and surface measurement represents the limit of what battery-powered missions can achieve at Titan. Any longer mission, any deeper investigation requires different power sources. The lesson is consistent with what we have already established. Working in the outer solar system requires nuclear power, because no other power source can sustain operations across the necessary durations. Solar power is insufficient. Battery power is insufficient for anything beyond brief surface phases. Even RTGs, while reliable, produce only modest power outputs. A mission that wants to do serious work at Titan, or anywhere else in the Saturn system, has to plan around these constraints from the outset. For human missions, the implications of Huygens are also worth noting. The probe was designed by the European Space Agency in collaboration with NASA and represented a major scientific achievement. It cost approximately €350 million to develop and operate. For a probe weighing 318 kilograms, designed for 90 minutes of surface operation, a human mission to Titan would weigh tens of thousands of kilograms at minimum, would need to operate for years rather than minutes, and would require power, propulsion, life support, and infrastructure orders of magnitude beyond what Huygens carried. The cost would be correspondingly larger, and the success criteria would be different. Huygens was successful if it landed and transmitted data. A human mission is successful only if the crew can live, work, and eventually attempt return, with all the complications that involves. There is no current funded plan for any follow-on mission to Titan that includes humans. Dragonfly, scheduled for arrival in 2034, is a robotic rotorcraft. It will land at Titan, fly between sites, and operate for several years using its nuclear power source. It is the most ambitious Titan mission ever conceived, and it will still be a robotic probe. 20 years after Huygens, and we are sending a more capable robot, not humans. The reasons are the same reasons that everything we have discussed so far points to: distance, duration, power, cost, and, ultimately, the return problem that we have not yet fully unpacked. There is, however, one more moon worth understanding before we get to that. Because the moon that has captured the most scientific imagination at Saturn is not Titan, despite Titan's complexity. It is the much smaller, much colder, much stranger Enceladus. Enceladus is small, only about 500 kilometers in diameter, roughly the size of an average European country, By the standards of moons in the outer solar system, Enceladus is unremarkable. It is mostly ice, with a thin coating of fresh snow that makes it one of the most reflective bodies in the solar system. It orbits Saturn at about 238,000 kilometres above the planet's centre, about the same distance Earth is from the Moon. For most of the decades after its discovery by William Herschel in 1789, Enceladus was considered a minor object, a small icy moon. Nothing particularly interesting. That changed in 2005. In July 2005, during one of Cassini's early flybys, the spacecraft's cameras spotted plumes erupting from Enceladus's south polar region, jets of water vapor and ice particles shooting hundreds of kilometers into space, originating from a region of long parallel surface fractures that scientists named tiger stripes. This was unexpected, to put it mildly. A small icy moon hundreds of millions of kilometers from the Sun was actively venting material from its interior. Active geology. Internal heat. Liquid water beneath the ice. None of this was supposed to be possible at a body Enceladus's size, far from any heat source. Cassini was redirected for additional flybys, more than 20 over the following years. Each pass revealed more detail. The plumes were composed primarily of water vapor, with significant amounts of carbon dioxide, methane, ammonia, and trace amounts of more complex organic compounds. The water contained salts, suggesting interaction with rock at depth. The plumes were powered by a sustained source of energy, almost certainly tidal heating from Saturn's gravity flexing Enceladus's interior. The source of the plumes was a global ocean of liquid water beneath the icy surface. The ocean, models suggested, lay perhaps 5 to 30 kilometers below the surface, with the ice shell varying in thickness around the Moon. The ocean was global, surrounding a rocky core. It was kept warm by tidal heating, possibly assisted by chemistry in the rock-water interface. This was the first time in the history of space science that an active subsurface ocean had been confirmed at any body other than Earth, and the first time that ocean material had been sampled. The plumes essentially deliver Enceladus's ocean to space, free of charge. Cassini flew through the plumes multiple times, including a deep flyby in October 2015 that took the spacecraft within 49 kilometers of the surface, directly through the plume material. The instruments analyzed what they captured. What they found was that Enceladus has the basic ingredients for life: liquid water in contact with rock, providing the right chemistry for hydrothermal interactions, carbon in the form of carbon dioxide, methane, and complex organic compounds. Sources of energy in the form of tidal heating and probably hydrothermal vents at the ocean floor. Conditions, in short, that on Earth support entire ecosystems independent of sunlight. Whether Enceladus actually hosts life is unknown. Cassini was not designed to detect life. It was designed to characterize the Moon and its environment, which it did with remarkable success. To actually search for life requires future missions, with instruments specifically designed for biosignature detection. Several such missions have been proposed. The most thoroughly studied is the Enceladus Life Finder concept, which would orbit Enceladus, sample its plumes in detail, and search for biological signatures using mass spectrometry and chemical analysis. The mission has been studied at various levels of detail since the 2010s, but has not been formally funded by any space agency as of 2024. A more ambitious concept involves landing on Enceladus and drilling through the ice to the ocean below. This is, however, an engineering challenge of staggering complexity. The ice shell is several kilometers thick. Drilling through it requires equipment, power, and time that exceed any robotic mission currently capable of being delivered to the outer solar system. The drilling itself would take years. The conditions, with surface temperatures around 200 degrees below zero and the need to operate continuously across that drilling period, are beyond current robotic capability. For human missions, the appeal of Enceladus is obvious. The chance to investigate, in person, a place where life might exist independently of Earth would be a scientific milestone unprecedented in human history. But the challenges of getting there and getting back multiply every challenge we have already discussed about Saturn. Enceladus is a destination that even probes cannot easily reach. Humans, in any reasonable planning horizon, are nowhere on the schedule. But Enceladus exists. Its ocean exists. The possibility of life there exists. And these possibilities are why, despite everything that argues against it, the conversation about reaching Saturn continues, because the destination, if anyone can reach it, may include answers to questions that humans have asked for as long as we have been able to ask questions at all. Which makes the return problem all the more poignant. Whatever the first humans at Saturn might find, the question of whether they get to bring the discovery home becomes urgent in a different way. Reaching Saturn is hard. Reaching one of Saturn's moons from orbit around Saturn is an entirely separate problem layered on top. The Cassini mission illustrated this clearly. The spacecraft arrived at Saturn in 2004 and entered orbit. From orbit, it conducted dozens of flybys of various moons, each one carefully planned to use the available delta-V in the spacecraft's remaining fuel. To reach Titan, Cassini had to perform engine burns that took it from one orbital trajectory to another, adjusting its path to pass close to the moon. To reach Enceladus, similar maneuvers were required. Each moon flyby cost fuel. Each fuel burn limited what was possible in the rest of the mission. For Cassini, this was manageable because the spacecraft was simply passing close to the moons. It did not need to land. It did not need to slow to orbital velocity around them. It just needed to fly past, take data, and continue on its way. The fuel cost of flybys is modest compared to the cost of true rendezvous. For a mission that wants to actually land on a moon, the fuel cost becomes severe. Consider Titan. To land on Titan from orbit around Saturn, a spacecraft must first decelerate from its Saturn orbit velocity to match Titan's orbital velocity. This requires a fuel burn. Then, to descend from Titan orbit to the surface, the spacecraft must slow further, since Titan's atmosphere will help with some of the deceleration, but a controlled landing still requires propulsive maneuvering. Then, on the surface, the lander has to operate for whatever the mission duration is. If anyone wants to leave Titan after the surface mission, the entire process reverses. Liftoff from the surface to orbit around Titan requires a substantial velocity change, perhaps 1.5 kilometers per second for Titan's gravity and atmospheric resistance. Then, to leave Titan orbit and return to Saturn orbit, another burn. Then, to escape Saturn's gravity and return to Earth, more burns. Each of these burns requires fuel. The fuel has to be either carried from Earth, which multiplies the total launch mass enormously, or manufactured locally, which requires equipment that has never been demonstrated at the necessary scale. For Enceladus, the situation is in some ways simpler and in other ways more complex. Enceladus has weaker gravity than Titan, so the fuel cost of landing and lifting off is lower, but Enceladus has no atmosphere to assist with descent or to fly through. All maneuvers must be entirely propulsive. The lower gravity helps. The lack of atmosphere makes the descent profile more challenging. In either case, a mission to land on a Saturn moon and return is, in effect, two missions stacked on top of each other. The first mission gets you from Earth to Saturn orbit. The second mission, conducted from Saturn orbit, gets you to the moon, onto its surface, off its surface, and back to Saturn orbit, from which the return journey to Earth begins. Each phase requires its own propulsion budget, its own life support, its own operational procedures. This is why every serious Saturn mission concept assumes a multi-vehicle architecture. The main interplanetary spacecraft, the one that crosses the distance between Earth and Saturn, is one vehicle. A separate lander or descent vehicle is required for each moon being explored. These vehicles must be carried as cargo on the main spacecraft, deployed at the right time, and either left behind after their missions or maintained for reuse. For Cassini, the answer was straightforward. The mission carried one lander, Huygens, designed for one descent to one moon. Once Huygens was deployed and its mission completed, no further surface operations were possible. The rest of the mission was orbital. For a human Saturn mission, the architecture would have to be substantially more complex. Multiple landers, multiple destinations, each requiring fuel, life support, and operational time. The crew, throughout this, would spend most of their mission in orbit around Saturn, with brief surface excursions to specific moons. The home base for the entire mission would be the orbiting spacecraft, which itself would need to be sustained for years of operations in the Saturn system. The complications compound. The propulsion requirements grow. The mission duration extends. The probability of failure across the multiple phases increases. And throughout all of this, the spacecraft is far from Earth, with communication delays of more than an hour, no possibility of immediate help, and a power and life support situation that has to be sustained by the systems aboard. This is what a Saturn mission actually looks like at the planning level. Not a single trip to a single destination, but a complex operation with multiple phases, multiple vehicles, and multiple opportunities for things to go wrong. And the power situation, which we have touched on briefly, is one of the most constraining factors of all. At Earth's distance from the Sun, solar panels produce a particular amount of electricity per square meter. The Sun delivers, on average, about 1,360 watts of power per square meter to a surface in space oriented perpendicular to the solar direction. This number, called the solar constant, is the foundation of every solar-powered spacecraft operating in the inner solar system. Solar power scales with the inverse square of distance from the Sun. Move twice as far from the Sun, and you receive a quarter as much sunlight. Move 3 times as far, you receive a ninth. Move 10 times as far, you receive 1/100th. Saturn orbits the Sun at approximately 9 times, 5 times Earth's distance. At Saturn's distance, the solar constant is approximately 15 watts per square meter, about 1% of what is available at Earth. This single fact rules out solar power for any serious mission at Saturn. A spacecraft that would need 1,000 watts of power at Earth, which is roughly the power consumption of a refrigerator, would need 100,000 watts worth of solar panel area at Saturn to produce the same electricity. The solar panels would have to be 100 times larger. At Saturn's distance with the necessary structural support and pointing requirements, this becomes prohibitive. This is why every spacecraft that has ever operated at Saturn has used nuclear power. The Pioneer 11 mission in the 1970s used RTGs. Voyager 1 and Voyager 2 used RTGs. Cassini used 3 RTGs. Cassini used 3 RTGs, providing a combined initial power of 885 watts. The Huygens probe, which had a brief operational lifetime, used batteries. Radioisotope thermoelectric generators are reliable, but they have limitations. They use the natural decay of plutonium-238 as a heat source, and they convert that heat to electricity using thermocouples. The conversion efficiency is low, about 6 to 8%. Most of the heat produced by the plutonium is wasted as thermal radiation. The total power output is modest. 3 RTGs producing 885 watts is the kind of power output that an industrial laboratory might use for a single instrument. RTG power output also degrades over time. The plutonium decays, producing less heat each year. The thermocouples themselves slowly degrade. Cassini's RTGs, producing 1,885 watts at launch, were producing about 633 watts by 2017, a loss of approximately 28% over 20 years. The decay rate is predictable. Mission planners account for it in advance, but it means that a longer mission has less power available later, just when more redundancy and more capability might be needed. For a human mission, the power requirement is fundamentally different. A crew of 4 or 6 humans requires not 885 watts, but kilowatts or tens of kilowatts of continuous power for life support alone. Adding scientific instruments, communication, propulsion, and habitat systems pushes the requirement higher. For a Saturn mission that might run for 14 to 18 years, the power source must produce these high levels of power reliably throughout that duration in the cold and isolation of the outer solar system. The only practical option is a nuclear fission reactor. Not the radioisotope decay of an RTG, but actual nuclear fission, similar to what powers submarines and aircraft carriers. A small reactor of perhaps 100 kilowatts of electrical output, scaled down for spacecraft use, would provide the power needed for a crewed Saturn mission. Such reactors have been studied. The Kilopower project, conducted by NASA from 2015 to 2018, developed and ground-tested a small fission reactor design. The K-Rystite reactor, built and operated successfully during that project, produced about 1 kilowatt of electricity from a uranium core about the size of a paper towel roll. Larger versions in the 10 to 100 kilowatt range are theoretically straightforward to develop, but no such reactor has been built or flown. A flight-qualified nuclear reactor for spacecraft use is not a casual development project. It involves nuclear materials, regulatory approvals, environmental considerations for launch, and substantial engineering for the high-temperature, high-radiation environment that the reactor would create inside a spacecraft. The cost would be substantial, probably comparable to a major spacecraft mission in its own right. The timeline would be at least a decade, more likely 15 to 20 years. For Saturn missions, this is the bottleneck. Without nuclear reactors, crewed missions are impossible because the power required cannot be supplied. With nuclear reactors, missions become possible, but the reactor development is itself a massive undertaking that has not yet begun in any serious way for spacecraft applications. This is what supplying power to a crew across 14 years at Saturn actually requires. And the power problem is closely tied to the next, even more fundamental problem, because every system on the spacecraft, including the propulsion that would carry the crew home, requires its own supply of energy, stored in the form of fuel, that has to survive those 14 years intact. Cassini launched in 1997 with 2,978 kilograms of propellant. By the time the mission ended in 2017, the spacecraft had used 2,950 of those kilograms. The propellant lasted 20 years, which was the planned mission duration and more. This is what success looks like, in propellant terms, for an unmanned mission at Saturn. 20 years of operations on a fixed initial fuel load, with no resupply, no manufacturing, no replacement. The fuel was sized for the mission was sized for the fuel, and they ran out together at the planned end of operations. For a crewed Saturn mission, the fuel question becomes the central problem. A crewed mission must carry at launch from Earth all the fuel needed for the entire round trip. The fuel for Earth departure, the fuel for course corrections during cruise, the fuel for Saturn arrival, the fuel for moon flybys and landings if planned, the fuel for any orbital adjustments throughout the years-long stay at Saturn, and, critically, the fuel for the return journey to Earth. The fuel for the return journey is the largest portion of this total. Returning from Saturn requires escaping Saturn's gravity, which is substantial because Saturn is the second largest planet in the solar system. Escaping requires a delta V of about 36 kilometers per second from the planet's cloud tops. Much less from orbit, but still considerable. Then the spacecraft must travel back to Earth, using more gravity assists in reverse, which takes another 7 years and additional fuel for course corrections. Then it must enter Earth's atmosphere, slow down, and land or splash down safely. The total fuel required for a full round trip to Saturn is enormous. Mission concept studies that have looked at this in detail have generally concluded that the fuel mass for a crewed Saturn mission using current chemical propulsion would exceed the spacecraft mass by factors of 10 or more. The vehicle would be almost entirely fuel. This is where the Tsiolkovsky rocket equation, the same equation we discussed for Mars missions, becomes brutal. The fuel needed to achieve any given velocity change scales exponentially with the velocity itself. For interplanetary missions, the velocity changes are large. The fuel mass becomes enormous. And for a Saturn return mission, the fuel mass becomes effectively impossible at any reasonable spacecraft size. There are theoretical solutions. Nuclear propulsion, in the form of nuclear thermal or nuclear electric propulsion systems, could provide much higher fuel efficiency than chemical rockets. A nuclear thermal rocket, which uses nuclear fission to heat a propellant like hydrogen to high temperatures and expels it, achieves roughly twice the specific impulse of the best chemical rockets. This means roughly half as much fuel for the same delta V. Nuclear electric propulsion, which uses electricity from a nuclear reactor to accelerate ions to very high speeds, achieves specific impulses 10 to 20 times higher than chemical rockets. The fuel mass for a Saturn mission with nuclear electric propulsion would be substantially smaller than with chemical propulsion. The mission becomes more feasible. But nuclear propulsion is not currently available. Nuclear thermal rockets have been studied since the 1950s, but have never flown. Nuclear electric propulsion has flown on small unmanned probes for short missions, but never at the scale needed for crewed interplanetary flight. Both technologies require substantial development testing and qualification, before they could be used for human missions. In the absence of nuclear propulsion, the alternative is to manufacture fuel at the destination. This is essentially the same approach proposed for Mars missions, using local resources to produce return propellant. For Saturn, the obvious source would be Titan. Methane is abundant on Titan, both as atmospheric gas and as surface liquid. With electrolysis of water, ice, and chemistry on the methane, a fuel manufacturing facility on Titan could produce methane and oxygen, the same propellants used in modern rocket engines like SpaceX Raptor or the Blue Origin BE-4. Setting up such a facility on Titan, however, is a major project in itself. The facility must be landed on Titan, deployed, powered, and operated for years to produce the necessary fuel. Each of these steps has not been demonstrated. The mass of the facility would be substantial. The power source for the facility, presumably nuclear, would add more mass. The timeline would require the facility to be operational years before the crew arrives, and throughout these years the facility must function in Titan's extreme cold, exposed to methane rain, ice accumulation, and the slow degradation that affects any complex equipment over time. A failure of the fuel manufacturing facility at any point during its operation could mean that the crew, when they arrive, finds insufficient return propellant. The mission, at that point, becomes one-way by default, not by design. This is the central problem of any Saturn return mission. The fuel must either be carried from Earth, multiplying the mission mass beyond practical limits, or it must be manufactured at Saturn, which requires infrastructure that has never been built. The third option, nuclear propulsion, exists in principle but not yet in practice. Without solving this problem, return missions to Saturn are not just difficult. They are not really missions at all. They are concepts that the math has not yet allowed to become engineering. Return missions in interplanetary spaceflight are always harder than outbound missions. This is true for several reasons. The fuel must be carried for both directions, multiplying the total fuel mass. The vehicle must survive longer, which means more redundancy and more redundancy requirements. The crew must remain healthy across the full duration, which means more life support and more medical capability. And the trajectory planning must work in both directions, which means launch windows must align both ways. For Saturn, every one of these factors becomes worse than for inner solar system missions. The fuel doubling for outbound and inbound is more severe at Saturn than at Mars, because the velocity changes required at Saturn are larger. The escape velocity from Saturn itself is roughly 36 kilometers per second, compared to 5 kilometers per second for Mars. Even leaving orbit around Saturn, which requires less energy than escaping the planet's surface, requires more fuel than leaving Mars orbit. The fuel mass for return scales accordingly. The vehicle longevity requirement is worse at Saturn than at Mars. A Mars mission lasts about 2.5 years. A Saturn mission lasts 14 years or more. The probability of any given component failing across that duration is several times higher. Maintenance, repair, and replacement of failing systems becomes a continuous requirement throughout the mission. The crew must carry spare parts. The crew must include people with the expertise to perform repairs on every critical system. The crew must spend significant fractions of their time on maintenance rather than scientific work. The crew health problem is fundamentally different at Saturn. A Mars crew might lose 9 to 18% of their bone density during the outbound cruise. A Saturn crew, with a 7-year outbound cruise instead of a 9-month one, would experience proportionally greater losses at a continued rate of 1 to 1.5% per month in microgravity. 7 years of cruise would mean roughly 80 to 100% bone density loss. This is of course not a continuous linear process, and the body's response to long-duration microgravity has never been measured over 7-year durations. The losses might plateau at some level. They might continue at reduced rates. They might result in catastrophic skeletal weakening that would make any return to Earth gravity unsurvivable. We do not know. No data exists. The longest continuous human stay in space is roughly 437 days, set by Valery Polyakov on Mir in 1994 and 1995. Polyakov's recovery on return to Earth was difficult but successful. He needed extensive physical therapy. He regained mobility over months. but 437 days is approximately 1/6 of the duration of a Saturn outbound cruise. The biology of 7 years in microgravity is a research question for which we have no answer. The trajectory planning for return is worse at Saturn than at Mars. The launch windows for return from Saturn to Earth occur approximately once every Saturn orbital period, which is 29.5 Earth years. There is, in practice, more than one return opportunity within that period because the geometry of gravity-assist trajectories provides some flexibility, but the optimal return windows are constrained. Miss the optimal window and the next opportunity is years away. Each additional year of waiting at Saturn means more bone loss, more radiation exposure, more probability of equipment failure, more dependence on Earth-supplied resources. Compare this to Mars, where windows open every 26 months. A missed window at Mars adds 2 years to the mission. A missed window at Saturn could add years. There is also a subtler problem. The return cruise itself is 7 years. During this time, the spacecraft is moving through interplanetary space at high speed, but with limited capability to make course corrections. Cumulative effects of small errors over 7 years can result in significant arrival error at Earth. The navigation requirements for a precise atmospheric entry at Earth from a Saturn return cruise are demanding, requiring careful tracking and possibly multiple course correction burns spread across the years of flight. All of these factors combine to make Saturn return missions, in the language of aerospace engineering, concept-level only missions. They have been studied. The math has been done. The fuel requirements, life support requirements, vehicle longevity requirements, and trajectory requirements have all been calculated. The conclusion of these studies consistently is that crewed Saturn return missions exceed the practical capabilities of current and near-term technology by substantial margins. This is not a statement of impossibility. With significant technological development, particularly in nuclear propulsion and life support, crewed Saturn missions become technically feasible, but the development required is substantial. The cost would be enormous and the timeline would be measured in decades from now, not years. In the meantime, Saturn remains what it has been throughout the history of spaceflight, a destination for robotic exploration, with no realistic plans for human missions and no current development programs aimed at enabling such missions. And the biology, even for an unrealistic future mission with all the technology required, presents its own set of problems that no technology can fully solve. Consider what 14 years means for a human body. A person who leaves Earth at age 40 returns at age 54. A person who leaves at 35 returns at 49. Half a working life. More than a decade of physiological aging compressed into a mission, with the additional stress of microgravity, radiation, isolation, and confinement layered on top of normal aging. This is the timescale of a Saturn return mission. 7 years out, possibly several years of operations at Saturn, 7 years back. The total duration depends on the specific trajectory and the planned operations at Saturn, but 14 years is a reasonable lower bound for any realistic mission. For Mars, where the equivalent number is 2.5 years, the biological considerations have been studied in detail. Bone loss, muscle atrophy, cardiovascular changes, radiation exposure, all have data from ISS missions and analog studies. The numbers, while concerning, are bounded. Astronauts have spent up to 1.5 years in space. The biology can be modeled with reasonable confidence. For 14 years, the biology is in a regime that no human has ever experienced. The longest continuous human spaceflight, 437 days for Polyakov, is 1/12 the duration of a Saturn return mission. The cumulative effects of microgravity, radiation, and isolation across 7 years of outbound flight, several years at Saturn, and 7 more years of return flight are not in any current dataset. There are a few things we can predict with confidence. Cumulative radiation exposure over 14 years would be enormous. Bone loss, even with countermeasures, would be substantial. Muscle atrophy, cardiovascular deconditioning, and psychological stress would compound across the mission. The crew would, by the time they returned, have spent more time in space than any human in history, possibly more than the combined experience of all astronauts who have ever flown. The question of what survives this experience is genuinely unknown. We do not know, for instance, whether a human body can maintain functional health for 14 years in microgravity, even with intensive exercise and medical countermeasures. We do not know how the immune system responds to that duration of exposure to space conditions. We do not know how mental health, sleep patterns, cognitive function, and personality stability hold up across a mission longer than a typical academic career. What we know from analogues is limited. The Mars 500 study lasted 520 days. It was simulated, not actual space exposure, but it documented psychological strain and behavioral changes consistent with significant adaptation challenges. The crew, when they emerged from their simulated mission, were measurably different from when they entered. Not damaged, but adapted, in ways that suggest a real 14-year mission would produce profound and possibly permanent psychological changes. We also know from submarine crews, Antarctic stations, and other isolated long-duration assignments that humans can sustain operations in confined environments for extended periods, but generally with strong rotation policies, periodic relief, and known endpoints. A Saturn return crew would have none of these advantages. They would be the same 6 or 8 or 10 people in the same spacecraft for 14 years. No rotation, no relief, no certainty about return. This is the human dimension of the Saturn return problem. The mission, even if every technical challenge was solved, exposes the crew to a duration of confinement and physiological stress that no human has ever survived to study. The first crew to attempt this would be experimenters as well as explorers. They would be discovering in real time what 14 years of deep space exposure does to human beings. The medical implications of any return are also profound. A crew that has spent 14 years away from Earth, including 7 years of return cruise in microgravity, would arrive in physical condition that no medical team has prepared to receive. Their bones would be severely demineralized. Their muscles would be atrophied to a degree unprecedented in spaceflight medicine. Their cardiovascular systems would be calibrated to microgravity. Their immune systems would have been operating in conditions far from Earth's microbial environment. Recovery on Earth would not be a matter of weeks. It would be a matter of years, possibly with some functions never returning to pre-mission levels. The crew might never walk normally again. They might require permanent medical assistance for basic activities. They might place significantly elevated cancer risk for the rest of their lives because of the cumulative radiation exposure. These are not certainties. They are reasonable extrapolations from current spaceflight medicine. They could be better or worse than the projections, depending on factors we do not yet understand. But they are the realistic medical expectations for a Saturn return crew, and the question of whether returning to Earth is the right choice for crew members in this condition becomes complicated. Some might prefer to remain in lower gravity, perhaps at Saturn or in transit between worlds, where their adapted bodies are more functional. Some might choose Earth despite the difficulty, because Earth is where home and family are. The choice, when made, would be intensely personal and unlike anything any astronaut has ever faced. This is what 14 years of Saturn mission means for the body that has to live through it, and it brings us to the radiation dimension which compounds everything else. Galactic cosmic rays are the universal background of high-energy particles streaming through interstellar space. They originate from supernova explosions, active galactic nuclei, and other high-energy astrophysical events. They travel through space at velocities close to the speed of light, and they penetrate ordinary matter with relative ease. On Earth's surface, we are protected from most galactic cosmic rays by 2 layers of shielding. Earth's magnetic fields deflects many of them away from the planet entirely. The atmosphere absorbs most of those that get through, with cosmic ray flux at sea level reduced to a small fraction of what it would be in space. In interplanetary space, neither protection exists. A spacecraft and its crew are exposed to the full cosmic ray flux of the galaxy. The exposure rate is far higher than on Earth, far higher than even on the surface of Mars, and the cumulative dose over long durations becomes substantial. For Mars missions, where the crew's duration is about 9 months each way, the total radiation dose for a round-trip mission is approximately 1 sievert. This is the number that, as we discussed earlier, exceeds NASA's career exposure limit for astronauts. For Saturn missions, the crew's duration is approximately 7 years each way, with several years of operations at Saturn in between. The total cumulative cruise time alone is about 14 years. The cumulative dose at galactic cosmic ray exposure rates in deep space would be in the range of 5 to 8 sieverts depending on solar cycle conditions and shielding effectiveness. 5 to 8 sieverts is a radiation dose with severe medical implications. At doses of 4 to 5 sieverts, acute radiation syndrome becomes likely if the exposure is over a short period. At doses of 8 sieverts or more, mortality from acute radiation poisoning is high even with medical treatment. The Saturn cruise exposure would be spread across years rather than minutes, so the body's repair mechanisms have time to address some of the damage, but the cumulative effect is still profound. The lifetime cancer risk associated with cumulative doses of 5 to 8 sieverts is substantial. By current estimates, it would increase the lifetime fatal cancer risk by 25 to 40% above baseline, possibly more. The crew would arrive back at Earth, or attempt to, with the equivalent of decades of accelerated cancer risk added to their normal aging. This is not a small effect. It is a fundamental health consideration that any realistic Saturn mission must grapple with. Saturn itself adds its own radiation environment. Saturn has a substantial magnetic field, similar in nature to Earth's but proportionally weaker. The magnetic field traps charged particles and radiation belts, similar to Earth's Van Allen belts but extended over a larger volume. Spacecraft operating in close proximity to Saturn, particularly during ring plane crossings or moon flybys, can experience significant radiation exposure from these trapped particles. Cassini, during its grand finale phase in 2017, when it flew between Saturn and its inner rings, encountered particle environments that were carefully studied and managed. The spacecraft had to dive through the gap between Saturn and the D-ring 22 times. Each pass exposed it to radiation that the spacecraft's components could tolerate, but that would have been concerning for a crewed mission. The radiation belts at Saturn are not as intense as Jupiter's, which would be even worse, but they are still significant. For a crewed mission, the time spent in close orbital proximity to Saturn would need to be carefully managed to avoid the worst of the trapped radiation. Operations near the rings would be limited. Flybys of certain moons, particularly Enceladus, would need to consider the radiation environment as well as the operational requirements. Shielding against galactic cosmic rays is, as discussed earlier, fundamentally limited. The cosmic rays are so energetic that conventional spacecraft walls do not stop them, and in some cases make the problem worse by producing secondary radiation. The only effective shielding is substantial mass, on the order of meters of water or hydrogen-rich material. For a Saturn cruise lasting 7 years each way, the shielding mass would need to be substantial. There is some research into active shielding using magnetic fields generated by superconductors, which could deflect charged particles around the spacecraft. This research is at very early stages and no operational system exists. For practical missions in the next several decades, the radiation exposure will be what the cumulative cruise time produces, with whatever passive shielding can be afforded by mass budgets. This is the radiation reality of a Saturn mission. 14 years of accumulated exposure that would, in itself, constitute one of the most severe environmental conditions any human has ever endured. The biology of surviving that exposure and remaining functional at the end of it is at the edge of what current medicine and biology can predict. Microgravity causes bone loss. We have discussed this in the context of Mars missions. The rate is approximately 1 to 1.5% per month for weight-bearing bones, slower for non-weight-bearing bones. For a 9-month Mars cruise, the resulting bone loss is in the range of 9 to 18%, significant but recoverable with extensive rehabilitation and bounded. For a Saturn cruise lasting 7 years one way with 7 more in return, the cumulative microgravity exposure is approximately 15 times longer. The bone loss, if rates continued at the ISS measured pace, would be catastrophic. At 1% per month for 14 years of cruise time, the loss could theoretically reach over 100%, which obviously is not a physical possibility because there is a floor at 0. The actual progression is more complex. What likely happens during very long microgravity exposure is that bone density decreases rapidly at first, then plateaus at some lower level. The exact shape of this curve and where it plateaus is unknown because no human has been in microgravity long enough to find out. Models based on ISS data suggest that the plateau might be reached after 1 to 2 years, with bone density at perhaps 60 to 70% of pre-mission levels. Whether the plateau holds beyond that, or whether progressive loss continues at a slower rate, is unknown. What is known is that a 30 to 40% reduction in weight-bearing bone density is medically severe. On Earth, a person with that level of bone density has osteoporosis. The bones are brittle. Minor falls can result in fractures. The hip, the spine, and the wrist are particularly vulnerable. The condition typically requires medical management, including bisphosphonate drugs, weight-bearing exercise, and careful avoidance of fall risks. For a Saturn crew, the issue is more acute because they would experience this level of bone loss not from aging, but from environmental exposure at a younger age, with no opportunity for the usual countermeasures. Exercise can slow but not prevent bone loss in microgravity. ISS astronauts spend approximately 2 hours per day on resistive exercise equipment specifically designed to provide mechanical loading to weight-bearing bones. The exercise reduces bone loss but does not eliminate it. After 6 months, even with intensive exercise, measurable bone loss occurs in nearly all astronauts. Drug interventions, including bisphosphonates and newer drugs that target bone metabolism, have been tested in spaceflight settings. They show some effectiveness in reducing the rate of loss, but they do not stop the loss, and they cannot be sustained indefinitely without side effects. For a 14-year mission, the cumulative bone loss, even with the best countermeasures, would likely leave a 40-year-old astronaut with the bone density of a 70-year-old. The muscle atrophy similarly would be significant. The cardiovascular system would be deconditioned. The whole body would have aged, biologically, decades beyond the chronological age. This means that the crew, by the time they reach Saturn, would already be in a physical condition that no astronaut has ever been in. They would have to perform the operations of the Saturn mission in this condition. The surface excursions, if any are planned to moons, the maintenance work, the scientific observations, the emergency response, all of it would have to be done with bodies that have aged the equivalent of decades during the cruise. Return to Earth, in this condition, becomes a serious medical question. Earth's gravity, applied to a body that has lost half its bone density, would impose stresses that the skeleton might not tolerate. Standing might be impossible without exoskeletal support. Walking might cause fractures. The cardiovascular system might not be able to maintain blood pressure against Earth gravity. Recovery on Earth would be a multi-year medical project, with no certainty of full restoration. Some have suggested that crew members on long-duration missions might prefer not to return to Earth because the medical reality of return would be more difficult than continued life in low gravity. This is not a fanciful suggestion. The biology actually supports it. A crew member adapted to microgravity for 14 years might function better remaining in microgravity than attempting to react to Earth's gravitational pull. This adds another dimension to the question of whether the first humans to reach Saturn will return. The biology might make return undesirable, even if the engineering allowed it. The crew might choose for medical reasons to live out their lives in space or at a low-gravity environment, rather than face the medical consequences of a return to Earth. The crew, in other words, might decide that the cage of compounding constraints is preferable to the alternative. And this is one of the most subtle reasons why Saturn return missions are not really planned at any serious level. The crew, by the time they could return, might choose not to. The psychological dimension of a Saturn mission is in some ways the dimension we know least about. We have data on bone loss. We have data on radiation exposure. We have data on cardiovascular adaptation. We have decades of measurements from astronauts and cosmonauts in various space environments. But we do not have data on what happens to human psychology over 14 years of confined, isolated, distant operations far from Earth. The closest analogues are limited. The Mars 500 study, lasting 520 days, documented significant psychological effects in its volunteer crew. Sleep increased on the simulated return leg. Activity levels decreased. Interpersonal frictions emerged. The crew, while professional and competent throughout, exhibited measurable adaptation challenges. But 520 days is approximately 1/10 the duration of a Saturn outbound cruise alone. The psychology of 14 years, with several of those years spent at Saturn rather than in cruise, is not in any current dataset. Submarine crews provide some perspective. Submarines on extended missions can spend 3 to 6 months underwater, with limited communication, no natural light, and confined quarters. The crews report psychological effects including sleep disturbances, mood changes, and interpersonal stress. These effects are managed through training, careful crew selection, and the knowledge that the mission has a defined endpoint. Antarctic research stations provide another analogue. Winter rover crews spend 6 months in extreme isolation, often with no possibility of evacuation during the polar winter. They experience similar psychological effects to submarine crews, including some that are unique to their environment, such as the so-called T3 syndrome of cognitive slowing associated with prolonged low light exposure. In all of these analogues, the duration is months to a year. The Saturn case requires extrapolating across more than a decade. The crew of a Saturn mission would face a unique psychological situation. They would be the most physically isolated humans in history by orders of magnitude. They would experience communication delays of more than an hour each way, making real conversation with Earth impossible. They would know that their mission would not end for years. They would know that emergency assistance from Earth was, in any practical sense, unavailable. They would also know that they were aging, that their bodies were changing, that whatever they had planned to do with their lives back on Earth was on hold, possibly indefinitely. They would receive messages from family describing the lives of children growing up, parents aging, friends marrying, sometimes dying. They would not be present for any of it. They would respond to these messages, knowing their responses would arrive weeks later, knowing that the events they were responding to were already weeks in the past from the perspective of the sender. This is a kind of temporal isolation that no human has experienced before. The mission would unfold across years, but the communication with Earth would always be lagged. The crew would live in a perpetual present, with the past always slightly behind and the future always uncertain. How a human mind responds to this kind of sustained displacement is unknown. Some psychological adaptations are predictable. The crew would form intense bonds with each other, because they would be all they had. They would develop routines and rituals that gave structure to the otherwise undifferentiated passage of time. They would, possibly, develop psychological strategies that closed off active longing for Earth in favor of full attention to their immediate environment. Some adaptations might be less healthy. Crews on long-duration missions sometimes experience interpersonal conflicts that escalate over time. They sometimes develop psychological symptoms similar to depression or anxiety. They sometimes lose interest in mission objectives, sliding into apathy or focusing on small concerns at the expense of larger ones. Without external intervention, these dynamics can become difficult to manage. For a Saturn crew, the lack of external help is the defining constraint. There is no flight surgeon on Earth who can directly intervene. There is no psychiatrist available for real-time consultation. There is no possibility of rotating the crew. The crew that boards the spacecraft is the crew that completes the mission or does not. This is why some mission concepts for very long-duration missions consider the possibility of putting crew members in some form of hibernation or torpor for portions of the mission. Reducing metabolic activity during the cruise phases could reduce some of the medical and psychological stresses. But hibernation in humans is not a current medical capability. It exists in some animals, but not in our species, and the research into induced human torpor is in early experimental stages. For practical Saturn missions in the foreseeable future, the crew would be awake, conscious, and confined to a spacecraft for 14 years. The psychological reality of this is something we cannot fully predict. We know it would be hard. We know that some people somewhere would attempt it. And we know that what they experience would be different from anything any human has ever experienced before. Throughout everything we've discussed about Saturn missions, the communication delay has been a recurring theme. 80 minutes one way, about 2 hours and 40 minutes round trip. For practical operations, this delay reshapes everything about how a mission functions. Consider a simple operational scenario. The crew has a question about a procedure. They send a message to Earth requesting clarification. 80 minutes later, Mission Control receives the message. The flight director reviews it. The relevant subsystem experts are consulted. A response is formulated. The response is transmitted. 80 more minutes pass. The crew receives the response. Total elapsed time, even in the best case, about 2 hours and 40 minutes. For a real working environment with shift changes, expert availability, and the normal back and forth of operational consultation, this can easily stretch to a working day. For routine matters, this is workable. The crew plans procedures in advance. They consult Earth in batched conversations, sending multiple questions at once and receiving multiple answers. The daily schedule is structured around long-duration tasks that can absorb the communication latency. They learned, over time, to think and operate at the cadence of the delay. For non-routine matters, the delay becomes a real constraint. Imagine an unexpected technical problem. A system has begun behaving abnormally. The crew investigates, but the cause is unclear. They have several possible courses of action, each with different risks and consequences. They want guidance from Earth before making a decision. They send a description of the problem. 80 minutes pass. Mission Control analyzes. Specialists are called in. A response is drafted. By the time the crew receives any guidance, 2.5 hours have passed since they first identified the problem. During those hours, the situation may have evolved. The crew may have had to make decisions on their own anyway because waiting was not an option. The Earth guidance, when it arrives, may be advising on a problem that no longer exists, or has worsened, or has been resolved. For a true emergency, the delay becomes effectively infinite. A medical emergency that requires immediate action cannot wait for 2.5-hour consultation. A mechanical failure that threatens the spacecraft cannot wait for ground analysis. The crew must respond in real time with the resources they have on board, using the expertise present in the crew itself. This is why Saturn missions, in any realistic conception, must be designed for crew autonomy. The crew is not a subordinate group taking instructions from Earth. The crew is, for all practical purposes, an independent entity making its own decisions, with Earth providing strategic guidance and consultation that operates at the timescale of days rather than minutes. This is fundamentally different from any other crewed spaceflight. Apollo astronauts on the Moon could consult Houston in real time. ISS crews can consult flight controllers within seconds. Mars crews, with 3 to 22-minute delays, can have conversations that take hours, but are still conversations. Saturn crews would operate in something more like the relationship between an Antarctic winter overteam and their parent organization, where consultation is possible but cannot be relied on for immediate response. The crew must therefore be cross-trained to a degree that no current astronaut training program approaches. The crew must include medical capability, possibly multiple medical paracidals, engineering capability across all critical spacecraft systems, scientific capability for the mission objectives, psychological resilience, leadership ability, decision-making under uncertainty, all in a group of perhaps 6 to 8 people. The selection of such a crew would be one of the most demanding selection processes in human history. The qualifications would be extraordinary. The numbers of suitable candidates would be small. The training would be extensive, possibly years of preparation specifically for the mission, and after all of this preparation, the crew would still face situations that no preparation could fully anticipate. The mission would inevitably encounter conditions and decisions that fall outside the training. The crew would have to improvise. They would have to trust their judgment. They would have to operate, in the most literal sense, without the safety net of immediate ground support. This is the operational reality of being 80 minutes from help. It is not just a delay in conversation. It is a fundamental restructuring of how human missions work. The crew becomes, in effect, a small civilization, complete in itself, with Earth as a distant collaborator rather than a controller. For a 14-year mission, this restructuring would have to be sustained for the entire duration. The crew would have to maintain operational discipline, psychological cushion, technical competence, and mission focus across years, without the kinds of external feedback that normally help organizations remain effective. They would have to be, in some ways, more like a successful generational community than like a typical NASA mission team. It is a model of operations that humans have not really tried at this scale, in this kind of isolation, for this kind of duration. The first Saturn crew, when they go, will be inventing the model as they go. On September 15, 2017 at 4:55 a.m. Pacific Daylight Time, the Cassini spacecraft entered Saturn's upper atmosphere for the last time. The descent had been planned for nearly 2 years. As Cassini's fuel ran low in its main engine, mission planners had to decide what to do with the spacecraft at the end of its mission. The constraint was planetary protection. Cassini could not be allowed to drift indefinitely through the Saturn system because future scientific exploration of Titan and Enceladus, with their potentially habitable environments, could be compromised by contamination from a spacecraft that had been on Earth and might still carry biological material. The options were limited. Sending Cassini out of the Saturn system would require fuel that the spacecraft did not have. Crashing it deliberately into one of the moons would, ironically, create the very contamination the planetary protection rules were designed to prevent. Leaving it in a stable orbit was not really possible because gravitational interactions with moons would eventually destabilize the orbit, leading to an uncontrolled impact somewhere. The only option that protected the moons was destruction in Saturn itself. Saturn, with no possibility of microbial life surviving in its crushing atmosphere, was the only safe place for Cassini's final resting state. The decision was made to deliberately drive Cassini into the planet. The descent trajectory was carefully planned. Cassini had spent its final months performing what the mission team called the grand finale, a series of orbits that took the spacecraft through the previously unexplored gap between Saturn and its innermost ring. 22 such orbits were completed between April and September 2017. Each one provided unique data about Saturn's gravity field, atmosphere, ring composition, and magnetic environment. Data that had not been gathered in 20 years of operation, because the spacecraft had been kept away from this dangerous region until end of mission. On the final orbit, Cassini did not pull up. It descended directly into the atmosphere, oriented with its thrusters firing to keep its antennas pointed at Earth. The thrusters fought against the atmospheric drag, maintaining the orientation as long as possible. The spacecraft transmitted data continuously throughout the descent, sending back atmospheric measurements that no spacecraft had ever gathered. The radio signal from Cassini took 83 minutes to reach Earth. The team at JPL watched the signal fade as the spacecraft tumbled out of orientation, the thrusters unable to compete with the increasing atmospheric forces. Then the signal stopped. It was, by all accounts, an emotional moment. The team had worked with Cassini for over 2 decades. Some of them had been involved with the mission since before launch in 1997. They had grown up professionally with the spacecraft. They had watched it perform feats of science and engineering that none of them had thought possible. And they were watching in real time, but with an 83-minute delay, as it ended. The signal from the spacecraft is gone, and within the next 45 seconds, so will be the spacecraft itself. Program Manager Earl Mays announced when the data stopped arriving, "I hope you're all as deeply proud of this team and this accomplishment as I am. I'm going to call this the end of mission." The applause was muted. The end of Cassini was both a triumph and a loss. Within minutes of the signal ending, Cassini had broken up in Saturn's atmosphere. The spacecraft, which had been the size of a small school bus and weighed nearly 6 tons at launch, dissolved into the gas of the planet. The plutonium fuel from its RTGs, sealed in special protective casings designed to withstand atmospheric entry intact, would eventually fall into the deeper atmosphere, where it would be heated to the point of being incorporated into the planetary material. There is, in a real sense, no Cassini anymore. Its atoms are now part of Saturn. This is what we have done with every spacecraft we have sent to Saturn. They did not simply fly past. Pioneer 11 and the 2 Voyagers flew past and continued into deep space where they remain. Cassini, the only spacecraft to actually stay in the Saturn system, ended by being deliberately incorporated into Saturn itself. Not returned, not preserved, destroyed by design, because there was no other way to safely conclude the mission. The pattern is consistent. Saturn is a destination from which spacecraft do not return, not because we lack ambition, but because the physics of return, combined with the engineering requirements of the destination, make return missions impractical at every scale we have so far attempted. And the same pattern will apply when humans go. Different scale, same conclusion. The first humans to reach Saturn will arrive at a destination from which return, by any honest accounting, is not really part of the plan. There is a way of thinking about Saturn that emerges from everything we have discussed tonight. The distances are large, the journey times are long, the destination has no surface, the return fuel requirements are impossible at current technology. The biological costs of 14-year missions exceed anything humans have survived. The radiation accumulates to levels that would shorten the lifespans of returning crew members significantly. The psychological reality of confinement for that duration is in territory no human has ever explored. Any one of these constraints, in isolation, might be addressable with sufficient effort. Distance can, in principle, be crossed with better propulsion. The lack of surface at Saturn redirects missions to moons, which is workable. Return fuel can, in principle, be manufactured at Titan, given enough infrastructure. The biological challenges might be partially mitigated by future medical advances. The psychological challenges might be managed with improved selection and training. But together, simultaneously, all of these constraints converge to produce something that looks less like a difficult engineering problem and more like a feature of the universe itself. Saturn appears to be, in some operational sense, quarantined. This is not a statement about intent. The universe does not have intent. It does not arrange itself to prevent us from reaching things. But the structure of the laws of physics applied to the specific geometry of our solar system produces a result that functions as a quarantine. Saturn is reachable in principle, but the cost of reaching it, the cost of staying, the cost of returning, all combine to make sustained human presence there practically impossible across multiple compounding dimensions. The inner solar system, by contrast, is comparatively accessible. Mars is hard but possible. The Moon is straightforward. Earth orbit is routine. Within Mars's orbit, the universe has constructed an environment where human activity can be sustained, where return missions are feasible, where the basic project of exploration can proceed at scales that human institutions can support. Beyond Mars, the universe shifts. Distances multiply by factors of 6 or more. Mission durations multiply by factors of 10 or more. Energy requirements multiply by factors of dozens. Biological exposures multiply by factors of 15. Each variable that mattered for Mars becomes much worse at Saturn. And the costs compound in ways that make missions categorically different, not just incrementally more difficult. This pattern continues beyond Saturn. Uranus is twice as far as Saturn. Neptune is 3 times as far. Pluto is 4 times as far at average. For each of these worlds, the cost of reaching curve continues to rise, and the cost of returning curve rises even faster. By the time you reach the Kuiper belt, the asteroid-like region beyond Neptune, the math has become so brutal that no serious mission concept exists for crewed exploration. The universe, in other words, has constructed accessibility gradients that favor inner planets over outer ones, and that make the outermost regions of our solar system effectively unreachable for human missions at any scale we can currently imagine. This is not unique to our solar system. The same physics applies everywhere. Any planetary system organized like ours, with rocky inner planets and gas giants in outer orbit, would present similar accessibility patterns to any civilization trying to explore it. The accessibility gradient is a fundamental feature of how matter organizes itself around stars. For humans, the implication is that exploration has natural limits. We are not going to be able to reach everywhere we want to reach, not in any reasonable planning horizon, probably not ever for some destinations. The galaxy, never mind the rest of the universe, is mostly inaccessible to us, and likely will remain so. Saturn sits at one of the natural boundaries. Inside Saturn's orbit, the inner solar system, exploration is possible. Outside Saturn's orbit, exploration becomes a different category of activity, with costs that may not be supportable. So when the first humans reach Saturn, they will be reaching what may be the practical limit of human exploration in the next several centuries. They will be at the edge, the first humans to look at the planet Saturn with their own eyes, from somewhere in its system. The first humans to see Titan or Enceladus from close range. The first humans to know, by direct experience, what 80-minute communication delays mean. And they will be the first humans to face in person the practical impossibility of return, not as a theoretical limity, as the operational reality of their mission. they would have arrived at a place that the universe has quietly arranged to be a one-way destination by combining enough constraints that the math of getting back becomes impossible at every layer of consideration. This is what Saturn represents, not just a planet, a boundary, a line beyond which the universe stops being amenable to round trips, a place where the cage of compounding constraints becomes, for all practical purposes, indistinguishable from a true prohibition. The first humans to reach Saturn will know this when they arrive. They will have known it before they left, and they will have gone anyway, because that is what humans have always done at the boundaries of what is possible. Imagine standing on the surface of Titan. The temperature would freeze you instantly without protection, so you are wearing a heated suit with insulation rated for cryogenic temperatures. You are breathing from a tank. Because the atmosphere has no oxygen, your visor is treated to allow you to see through the orange-brown haze that fills Titan's sky. You look up. Above the haze, the sky is a deep brown-orange color, with patches of darker sky where the atmosphere thins. The sun, when visible at all, is a small bright disk, about 1/10 the size it appears from Earth, providing about 1% of the light intensity that Earth's surface receives. The day on Titan is dim, like a heavily overcast evening on Earth, but without the comfort of knowing the brightness will return. If conditions are right, you can see Saturn itself in the sky. Titan is tidally locked to Saturn, meaning the same side always faces the planet, similar to how Earth's moon always shows the same face to us. From the Saturn-facing side of Titan, Saturn dominates the sky. It appears as a vast crescent or full disk, depending on the orbital geometry, about 10 degrees across in angular size. By comparison, Earth's moon appears about half a degree across in our sky. Saturn from Titan is 20 times larger in angular diameter, with its rings often visible as a thin line across or above the planet's disk. This is a view no human has ever seen. The first crew to stand on Titan in protective suits would be looking at one of the most spectacular sights in the solar system. The planet they came to study, suspended above them in a haze-filled alien sky. They would also see Earth. Earth from Titan would be a faint bluish star, almost lost in the haze. Easy to miss against the background of the sky. At Saturn's distance, Earth has an apparent brightness similar to a moderately bright star, perhaps magnitude 4 or 5. Visible to the naked eye on a clear Earth sky, but barely. Through Titan's haze, it might be barely visible at all. That is the view of home. A faint star, nearly indistinguishable from any other star in the sky. The planet that contains everyone the crew has ever known. The cities, the oceans, the forests, the conversations, the history of everything that brought the crew to Saturn in the first place. All of it, compressed into a barely visible point of light. There is something almost philosophical about this view. From Earth, Saturn is a remote planet visible only with a telescope. From Titan, Earth is a remote planet visible only at moments of clarity, when the haze parts long enough for stars to appear. The relationship is reciprocal. Each world from the other is a point of light. The crew would experience this as a daily reality. They would step out of the habitat in their suits, perform their tasks on the surface or in nearby moons, and at moments when the work allowed, look up. Saturn would loom overhead. Earth would be somewhere in the sky hard to find. They would remember looking at it that they had been there once, that the place they came from was now reduced to a small light among other lights, and they would know, with the kind of certainty that 14 years of mission allows you to develop, that the small light was where they would not be returning to. Not because of any particular failure, because the mission they signed up for was, by its nature, a one-way mission. The first humans to reach Saturn would be the first humans to make a home, however temporarily, in the outer solar system. The view from Titan, if they ever achieve it, would be both a triumph and a quiet acceptance. Triumph because the human species had finally reached a destination beyond Mars, beyond the inner solar system, in the great outer reaches of our own system. Acceptance because that destination would also be, in every realistic accounting, where they would stay. This is what reaching Saturn would mean for the first humans to do it. Not a brief visit followed by a return. A new home, a new local environment in which to live out the rest of their lives, however long that turned out to be in conditions never tested before. And there would be people, knowing this, who would still volunteer, despite everything we have walked through tonight. The distances and the delays and the radiation and the bone loss, and the 14-year missions and the practical impossibility of return. There will be no shortage of volunteers. This is the strange, consistent pattern of human exploration. Whenever a destination becomes potentially reachable, even at enormous cost to those who would attempt it, people volunteer, often in significant numbers, often with full knowledge of the risks and the likely inability to return. The Polynesians, sailing across the Pacific in the centuries before written record-keeping, knew they were unlikely to return to wherever they came from. They went anyway. They built canoes, loaded them with families and supplies, and headed into open ocean. They reached Hawaii, New Zealand, Easter Island, dozens of other islands across millions of square kilometers of water. Many died on the way. Many ships were lost. The pattern continued for centuries because there was always a next generation willing to go. The Pilgrims on the Mayflower in 1620 did not have any reasonable expectation of return to England. The voyage took 2 months. The arrival was at a coast they did not know, in a climate they were unprepared for, among indigenous peoples they did not understand. Of the 102 passengers, roughly half died in the first winter. The survivors persisted. They were joined by additional ships. The settlement became permanent. The Bering Land Bridge crossings, perhaps 15,000 to 20,000 years ago, brought humans into the Americas in waves over thousands of years. The crossers had no way back. The land bridge eventually disappeared as sea levels rose. They were stranded in the Americas, and their descendants populated 2 continents over the following millennia. The crossing was one way by default. The settlers by necessity became Americans. This pattern repeats across human history. Every major migration of our species has been one way. The settlers did not return. They built. They had children. Their children had children. Their children had children. The places they reached became over generations the homes their descendants lived in. The aerospace engineer Robert Zubrin has spent decades arguing that the same pattern will apply to Mars and beyond. Zubrin's argument is that the impulse to settle new places is not a recent cultural development. It is a deep human pattern, present throughout our history, and almost certainly biological in some sense. Humans, given the opportunity, will go to new places. They will accept enormous costs to do so. They will not, in most cases, plan return trips. For Saturn, the case is similar, but more extreme. The duration is longer, the distance is greater, the infrastructure required is more demanding, but the basic pattern holds. When the technology eventually allows it, when the funding eventually permits it, when the mission architecture eventually becomes feasible, there will be volunteers, probably many of them. The 2013 Mars One project, despite its eventual failure for financial reasons, demonstrated this clearly. Over 200,000 expressions of interest were received from people willing to commit to a one-way mission to Mars. The mission was, as we now know, unrealistic at the time. The volunteers were responding to a possibility that did not exist, but the responses themselves were real. The willingness was real. For Saturn, the recruitment pool would be more selective. The qualifications would be more demanding. The mission would be longer and harder. But the willingness, when the opportunity arrives, will likely be similar. There will be scientists, engineers, doctors who recognize that the mission is one way, who understand the biological and psychological costs, who accept the impossibility of return, and who volunteer anyway. What drives this is hard to articulate cleanly. It is partly curiosity, the desire to know what is out there. It is partly the appeal of the unprecedented, the wish to be among the first to do something. It is partly the sense that the work matters in some way that transcends individual continuity. It is for some a way of dedicating a life to something larger than the life itself. The first humans to reach Saturn will be people who have made peace with these motivations. They will not be victims of the mission. They will be participants in it, knowing what it requires of them. They will have chosen the journey and the long stay and the lack of return deliberately and with awareness. This does not make the journey easy. It does not make the cage less real. It simply means that the cage is one the volunteers entered with their eyes open. They were not condemned to it. They walked into it because the journey was worth it to them. This is the human element that the technical analysis cannot capture. The mission is physically and engineering-wise close to impossible, but the people who would attempt it, if given the chance, would be motivated by reasons that physics and engineering cannot fully account for. They would go because going matters to them, even if returning does not. Throughout the history of human exploration, every generation has discovered limits. The early Polynesians, brilliant navigators that they were, reached the edge of their navigational technology somewhere in the Central Pacific. They settled the islands they could reach. They did not go further, because further was beyond the capabilities of the canoes and the navigation methods they had developed. The Vikings, in their longships, reached Newfoundland by way of Iceland and Greenland. They did not establish lasting settlements there. The distance, the supply chain, the climate, all combined to push them back to their North Atlantic strongholds. Their exploration peaked, and then contracted. The Spanish, Portuguese, English, French, Dutch, and other European maritime powers extended their reach across the globe in the centuries after 1492. They built empires, established trade networks, transformed the world. But even they had limits. The interior of Africa remained unmapped for centuries after the coasts were charted. The interior of South America was explored slowly. The Arctic and Antarctic regions were reached only in the late 19th and early 20th centuries. Every era of exploration, when looked at carefully, reaches some boundary. Beyond the boundary, the technology of that era cannot support further extension. The exploration program for that era has run its course. New technology, when it arrives, opens new boundaries. Old boundaries become routine. The cycle continues. For our era, the boundary appears to be Saturn. Within Mars's orbit, exploration is feasible. We have done it with robots. We are planning to do it with humans. The technology, the funding, and the political will are aligning to bring humans to Mars within the next few decades. The mission architecture is plausible. The challenges are severe but addressable. Beyond Mars, the gap to Saturn is the boundary. Saturn is reachable with current technology, but only barely, and only with robotic missions that are deliberately not designed to return. Crewed Saturn missions, for all the reasons we have discussed, exceed the practical capabilities of any technology we have or are developing in the near term. The energy requirements, the duration requirements, the biological requirements, all push beyond what current and proposed systems can support. This does not mean Saturn will never be reached. It does not mean that humans will never live in the outer solar system. It means that the current era of human exploration, the one that is bringing us to Mars and might eventually bring us to Saturn for brief robotic visits, has its natural endpoint somewhere around Saturn. Beyond Saturn, new technology will be needed. New propulsion methods, new life support systems, new ways of sustaining human presence across years that are not currently feasible. These technologies may emerge. They have always emerged at boundaries before. The question is the timeline. The Polynesians needed generations to extend their navigational capabilities to reach more distant islands. The European maritime powers needed centuries to bring exploration to its peak. We may need centuries to extend our exploration beyond Saturn, or we may find ways to compress that timeline. In the meantime, Saturn sits at the edge, the boundary of what is plausible for our era. The first humans to reach it will be reaching that boundary. They will be the explorers who go to the place that, for our generation, represents the limit. This framing has a particular kind of dignity to it. The first humans at Saturn are not failed Mars colonists who happen to go further. They are the explorers of the boundary. The first humans to reach what may be, for centuries, the practical edge of human spaceflight. Their mission is not a stepping stone to something easier later. It is the mission that goes as far as our generation can. There is something quietly satisfying about reaching the edge of what is possible, not in a defeated way, in the way that completed work is satisfying. The exploration has been carried as far as it can be carried with the tools available. The next era with new tools will carry it further. But this era has done what this era could do, all the way to its limit. For the first humans to reach Saturn, This is the meaning of their mission. Not a brief visit followed by return. The honest endpoint of an era of human exploration carried out by the people who agreed to be the ones to go to the edge. It is, in its way, a more honest mission than the round-trip alternatives that are not really feasible. The honesty is in accepting the constraints. The honesty is in going anyway. The honesty is in knowing that the mission is the limit of what humans can currently do, and doing it. We have walked tonight through what reaching Saturn actually means. We have looked at the distance, 1.43 billion kilometres on average, with significant variation, large enough that it changes the nature of every operational consideration. We have looked at the 7-year minimum journey time, the gravity assists required to make it possible, the empty space between Earth and Saturn that any spacecraft must cross. We have looked at the 80-minute communication delay which makes real-time conversation impossible and turns Earth into a distant collaborator rather than a present support system. We have looked at the power requirements that solar panels cannot meet, the nuclear technology that would be required, the fuel that must either be carried from Earth or manufactured at Titan. We have looked at the destination itself, Saturn, with no surface to land on, with crushing pressures at depth, with composition that destroys anything that descends into it. The moons that become the actual destinations. Titan, with its alien chemistry and stable surface liquids. Enceladus, with its hidden ocean and possible life. Each of these in its own way presenting challenges that compound the difficulty of the mission. We have looked at what 14 years of mission would do to a human body. The bone loss, the muscle atrophy, the radiation exposure that cumulatively would be in the range of 5 to 8 sieverts, the psychological strain of confinement and isolation for a duration that no human has ever experienced, the medical reality of return, which might leave the crew unable to function in Earth's gravity. We have looked at the engineering reality. The Mars Ascent Vehicle equivalent does not exist for Saturn at any scale. The in-situ resource utilization technology would need to be developed and demonstrated at Titan, which has never been done. The mass that would have to be landed on Titan or other moons for return infrastructure exceeds current capabilities by significant margins. The fuel for the return journey, even if everything else worked, is the central unresolved problem. We have looked at the economics. The Mars Sample Return mission, attempting to bring back a few grams of rock from Mars at an unmanned scale, was cancelled when its cost rose to $11 billion. A human Saturn mission, with its order of magnitude greater complexity, would cost a substantial fraction of an entire developed nation's annual budget. There is no current funding pathway, no current development program, no current schedule. And we have looked at the human dimension, the volunteers who would still go, knowing all of this, the frontier psychology that has driven every wave of human migration, the pattern of one-way settlements that defines virtually every successful expansion of human range, the Polynesians, the Pilgrims, the Bearing Crossers, the recognition that being the first to go somewhere has always involved accepting the impossibility of return. The conclusion that emerges from all of this is the title of tonight's conversation, Made Honest. The first humans to reach Saturn will not return, not because the universe physically forbids it, not because there is some absolute prohibition. The honest answer is more layered than that. The universe has constructed Saturn to be at the practical boundary of human exploration. The compounding constraints, the distance and the duration and the radiation and the energy and the biology and the economics combine into something that functions as a quarantine. Saturn is not unreachable. Saturn is just not returnable. The first crew to go will know this when they board the spacecraft. They will have signed up knowing it. They will have trained for it. They will have made their peace with the families they were leaving behind, the lives they were stepping away from, the planet they were unlikely to see again. And then, after 7 years of travel, they will arrive at the destination. They will see Saturn close up with their own eyes for the first time. They will see Titan from orbit, perhaps land on its surface and walk in its haze. They will see Enceladus, perhaps come close enough to sample its plumes. They will be the first humans to be present in the outer solar system, the first to extend human range beyond Mars. And then they will live there, for as long as their bodies permit, for as long as their supplies last. for as long as the missions sent after them continue to provide support. They will not come back to Earth. This is the honest journey, not a tragedy, not a heroic gesture, simply the structure of what reaching the boundary of human exploration actually requires. In this era, with these tools at these distances, the first humans to reach Saturn will be the explorers who agreed to be the ones to go there, knowing what going meant. They will see things no human has seen. They will know things no human has known. They will live in a place where Earth is a faint star in the sky, where Saturn looms overhead, where the sun is small and dim. They will adapt to the alien environment, build a small home in it, and continue the work of human exploration as far as the boundary allows. And when they look up, on a clear Titan day, when the haze parts long enough to see beyond the atmosphere, they will see the small blue star that is Earth. And they will remember that they were there once. And they will know with the kind of certainty that 14 years of mission allows you to develop that they are not going back. That may not be a tragedy. It may, instead, be the most honest journey humans have ever taken. The kind of mission that knows what it is from the beginning, accepts what it requires, and goes anyway. The first humans to reach Saturn will not come back. And in choosing to go knowing this, they will have done something that humans have done in different forms for as long as we have been human. They will have stepped into a new place and chosen against everything to make it home. The rest of the night is yours.